physics at the Texas A&M University.
Okay, thank you, Randy. Thank you for the invitation. I don't know how to get rid of that part. This meeting is being live streamed. So it means I have to touch here, maybe. Yeah. And well, I can get rid of that stuff in my computer, but not in the other.
How does he get?
Sorry, guys. I cannot advance the slides and I cannot get rid of that announcement. Yeah, but doesn't go now. Oh, okay. So we are in São Carlos, and we've been doing experiments with cold atoms for a long time. And this time we are doing some experiment with turbulence, which we are also doing for already some time. But now we are using this turbulent cloud, try to investigate some non-equilibrium properties of the system. So it's like having a prototype of non-equilibrium quantum system that we can produce the non-equilibrium and try to investigate the evolution of the non-equilibrium. So what I'm going to do is tell you a little bit how we evolve along those years, characterizing the turbulence. What are the main features? What remains in your system that is well known from turbulence in classical system, classical fluids? What's new, and how we are going from there? Okay, but before we are here to honor the memory of Hussein, and he was a great scientist and also a great man in Brazil. He's not Brazilian, but he adopted the spirit, and he was always there for trying to advance the culture of science, to try to convince authorities, try to evolve our own university. And he was part of my center as a theoretical support. And we did many discussions, and one of the papers I will show to you was inspired by Meir Hussein. So it is, of course, very bad that we don't have him with us anymore. But he did a very good contribution, and he left behind a whole group of people that has the same spirit, like one of the organizers of this meeting. Okay, so the experiment I'm going to show to you is a part of the group. We have a very large group. We're not doing only atomic physics. We're doing is a optical and photonic center that we do many experiments in biophotonics, in nanoplasmonics, and in atomic physics. And our laboratory is part of one. There is other laboratories. We have an atomic clock laboratory with fountain and other clocks. And we have another laboratory of Philippe Courtel doing experiments with scattering of light in cold atoms and things like this. But this experiment, what I'm going to show to you, has this group of people participating. Some of them you can see here in the audience. And you know, Lucas, Amilson, Gustavo, Patricia, which is here, and she's now a faculty of our institute. And Arnaud, we just graduate, and then all the rest are graduate students, and we have even the participation of a student that is located in Newcastle, Holly. And we have collaboration with many people. In the past, we had collaboration with even a large number. We still keep going with collaboration in many theoretical aspects with Professor Fetter from Stanford or Tsubota from Japan. But for the work I'm going to tell you, we have more collaboration with Ruati from Italy and the rest of the people from Newcastle. Oh, Patricia is here too. You are in many, many places, Patricia. And Thomas Kazenzer is a very interesting guy. He's in Germany, in Heidelberg, and he's one of the guys thinking very deeply on the non-thermal fixed points, which turbulent clouds may be a nice way to try to understand at least part of the time evolution of this non-equilibrium state. Okay, and we are a center. And what I'm going to do is I'm going to show you briefly how we excite. Yesterday we had the first talk saying that, well, let's shake things. Shake means introducing tiny rotations in many directions. This is what we do. And then we go from few vortices to turbulence. But we are very much interested in doing the turbulence. For how we got involved in this, well, I mean, we've been trying to excite condensate for a while. And then Tsubota published a paper and saying that, well, if you take the condensate and you give a rotation in many directions, you're going to generate vortices in many directions. And then that will evolve by reconnection to a turbulent state. And it's not so easy to keep rotating everything simultaneously, but we find a way. We call is inspired by the day-by-day life. We call quantum washing machine. So we do like a washing machine, because as you know, when you wash clothes, they don't rotate to wash, they shake. Because that's a way to generate turbulence and make sure whatever you put in the washing machine is getting closer to the cloth and remove the dust, remove whatever is there. So this is what we do. But we got involved because everybody says that, well, in quantum turbulence, word is simple and you can understand better the turbulence as a whole. And let me anticipate to you that after 10 years of characterizing everything, we realize that that's not true. But we do have a new system. And disorder in quantum system is, of course, one of the frontiers. We want to understand how time, how temperature, and how disorder play any role in this whole thing, right? We see the new models for cosmological models where they rely on turbulence to explain many of the things that are taking place, right? So it is a nice system independently of anything. And then we start to apply this, and this is what I'm going to do more or less. We already saw this kind of thing when you have turbulence in general. There are two important scales: the big one where you introduce, and the small one where the dissipation goes on. This is normally the two scales that people take care when dealing with the turbulence in classical fluid. When we go to the quantum fluid, there is an extra scale that will be very important. Let me anticipate to you, which is the distance between vortice filaments. So this distance is another scale that became very important, and I think is one of the main issues in producing some of the property we are able to measure. But, in the quantum world, we already saw this. We have a quantization of circulation, which means that our vortices are quantized, and high vorticity, high angular momentum per particle is not stable. The system decay. So normally you have a collection of single circulation, which means this n here, which is an integer of h over m, is 1. And when you have that, you have all the vortices equal in the system. That's simplify a lot what can happen, and you all know what can happen. If you put a lot of vortices, they crystallize. And when you look to a vortex, it's very nice because here, oh, by the way, we are experimentalists, but we have a group of theoreticians together, and we rely in two things. One we can see, which is the macro, is the density basically, and the time evolution, what we see. These are the two properties we somehow rely on to characterize this system. Well, we all know that wherever you have the rotation at the center, we have a zero density, and more or less the size of this is the healing length that we all learn, and we know that's depending on the interaction and the local density. So, because vortices are equal on a quantum system, at least when the high vorticity decay, I'm going to show experiment what we produce. By the way, one way of producing turbulence is produce a giant vortex and let it decay under some conditions that may produce turbulence as well. So I think in the classical system, you cannot spontaneously generate turbulence. If this morning you took your coffee and shake a little bit and let it go, it's not going to evolve to turbulence. You have to drive it a lot, then it drops will spill out as a result of turbulence. But in the quantum system, if you produce some situation spontaneously, it may evolve to turbulence. In a closed system like this, at least that's what we've been observed. Okay, well, there are many things related to vortices in quantum fluids. I'm not going to speak about this, and this is another perspective, is looking to those Abrikosov type of lattice and see how they can be perturbed. That's another thing. And by the way, this is a picture of one of our experiments, the sodium experiment, but we produce many vortices, but with the same sign. And but you have a very beautiful pictures along the last decade in the literature. Once you have vortices, they evolve, they react. There is a process, it's called reconnection. And by doing this reconnection, the messy part comes. And then you can see when lines that represent the vortices, they cross each other, they start to have this kind of bending. And then after many reconnections, you can see if two of these reconnect in the right place, we're going to make rings. And we make wiggles. Those wiggles are Kelvin type of oscillations that can be present. Is a way for the energy to be transferred to smallest and smallest scales. Okay, and I'm not going to have time to elaborate a lot about classical turbulence. Quantum turbulence, that's not new, right? People are studying turbulence in liquid helium for a long time. But when comes the condensates, we have more knobs to play with and different ways to excite and different ways to assist and different ways to extract information or to apply. Liquid helium, when you produce turbulence, it is a liquid helium with turbulent liquid helium. But when you have a condensate, you can let it go. You have matter waves propagating in space with some randomness on the phase and the amplitude, and that has equivalent to what we know in optics of coherent light, which is the speckle fields and things like this. So give us a chance to merge quantum liquids, quantum fluids with statistical quantum optics that is a very strong field and see similarities and everything. So I apologize, but I'm not be able to elaborate all those comparisons. But we do have some review papers, and Lucas is one of the co-authors with a nice one, where we discuss why all this is important, at least on our point of view. There is one thing that's very important on turbulence, either classical or quantum, which is the cascade. You inject energy at the large scale, small momentum, and that goes until it reaches the very tiny scale, the smallest possible scale in your system where dissipation takes place. And this process we call cascade. And in the middle of this, there is region where energy is not dissipated. This is an important characteristic of turbulence. It's called inertial range. So there is a range of scales or momentum where energy flows and go to the other end without dissipation. And this is an important thing because that's how the system really evolve in time, by producing those cascades. And there are a few cascades that are valid either for a quantum or classical system, or the end result is what's different, right? If you have a classical fluid, the dissipation takes care at the end of the thing. But when you have a quantum fluid, you're going to rely in sound, in phonons type of dissipation of the energy that you input. Okay, so our history on this field start more or less in 2010, where we were able to demonstrate in a BEC the presence, and then influence of so many people, and we try to expend a lot of time trying to characterize, seeing signature, measuring power spectrum, measuring population, measuring integrable length scale, trying to introduce entropy in the business to see if disorder was being installed, and so on. And up to here is what I call characterization of the system. And then we started to observe that we had a system that can go much beyond the understanding, but we can do many different applications. Speck of matter waves, non-thermal fixed points in the time evolution of those states after you excite, or even spontaneous generation, and many others that if I have time, I will introduce to you. There are different types of turbulence. You can excite a condensate in different ways. A vortex is a very nice topological type of excitation. And once you produce vortices, in some situations, they can tangle together, or not tangle, they can cluster together, make bundles. And of course, many quantum things together looks like classical, right? And this is similar to classical, and all the Kelvin cascade. People's been observing this in helium. Then there is divining, and another great scientist that we lost recently from England, right? It's called the super quantum, but actually it's vortices that can tangle and produce the turbulent. And we have also waves produced in the condensate that are very nonlinear interaction and among those modes, and then these evolve to reactions and turbulence as well. And this one also exists in the classical world, right? Just look at the ocean. When you fly with your plane, you're going to see the presence of wave turbulence in the surface of the ocean. Okay, we have two experiments dedicated to study this. One is the sodium, the other is the rubidium experiment. This is the rubidium experiment. And normally we excite, we see a few vortices, and then suddenly this evolves to turbulent, which looks like this in imaging, in absorption imaging. And this is the sodium. I want just to honor my people and my collaborators in the sodium experiment that's supposed to be a mixture to study turbulence and many other things. But at the moment, we're going to separate studies in sodium and potassium. And I don't know if Patricia will mention a little bit about her plans with the potassium here, but I hope so. And but sodium, we are doing some quenching, which is the opposite what we do to generate turbulence. And hopefully we're going to do something. Well, the main motivation is this. If you start with a condensate and you produce rotation in two directions, at least two. If you do only one, you're going to produce the lattice that we all know. But if you produce in two, there'll be reaction, and this will evolve. There are many ways to reach this. And the way we find out is, okay, well, let's introduce here on the potential. We have a Yaft-Preacher type of magnetic trap. We are now evolving to light traps for many reasons. And then we introduce deformations and rotations on the potential. And by doing that, of course, you go shaking. And I call this atomic washing machine. And that produces vortices. We spend some time investigating vortices. And then we're not investigating vortices anymore. We investigated the final result, produce the condensate, excite, holding time for a while for let the things evolve, observation. And what we observe everything that people has investigated already, like the scissor mold, which is evidence of superfluidity in this, and Chris Foote produced very nice work on that in the past, which is the bending of the axis of this, the asymmetry axis of the condensate. But then just go a little further, you're gonna see the vortices being formed. And once you see the vortices formed, there are a very nice simulation by Parker from Newcastle, where you see the vortices are formed at the edges and migrate in. Long ago, we were able to picture the vortices being formed, and then, of course, you have to make sure you produce vortices and anti-vortices, and we have done that by observing the tripole of vortices, which means that the only way to get some met-stable configuration of 3 vortices for a while if one is the opposite of the others. And then we did all this study. This is being published. So we are sure we produce vortices and anti-vortices. And as the amplitude of our excitation grows and the time of excitation, we make more vortices to go. This is amplitude. You know, we as experimentalists like to represent as a function of something we measure. And this is the volt, when we say amplitude millivolts, means what kind of current I pass to the extra coils, but this can be represented in terms of chemical potentials, for instance, how much energy I supposed to be putting there by those oscillations. And normally this is a few factors of the normal chemical potential of your sample. So it's not a lot of energy you are adding, but enough to make those excitations and to see their evolution. So once they evolve, we go and analyze by doing time of flight, because we don't have a resolution to do in situ. And normally we observe a nice evolution. Very soon we see no more vortices, very typical, they react. What we actually see is a big composition of apparently random fluctuations of the intensity or the density in our case. And of course, the phase there, because of all the reactions, is a kind of distributed along the sample. So that's a kind of evolution. It goes from few vortices to a very complicated cloud with a lot of perturbation, which we call turbulence. If you manage the amplitude of excitation and time of excitation, we were able to identify and simulate by 2 independent people, Tsubota in Osaka and Yukalov in Dubina, the same kind of behavior. They never predicted this last one, which we call granulation. We call granulation because we didn't have any other name to give, but maybe this is a breakdown of domains. You introduce so many random phases there that the system will say, hey, I can't hold this. It's better to have little islands of my condensate and behave that way. This is a domain that we never really went too deep through. Maybe now with Randy Hewlett in a more simple one-dimensional system, we may understand more of that. But you see, you can explore regular vortices, turbulence, or no vortices at all, only excitations that normally you do, depending on the combination of amplitude and time. And as you know, the product of this is related to how much energy you are inputting in the system. Okay, well, there are nice simulations being done in the past and now, and this is a work by people in Newcastle, where they simulate our excitation, and as you can see at the end, we see a collection of vortices and solitons being formed. So, and that's evolved. We don't detect the solid so well. I don't think we even detect the vortex so well. We detect the end of the excitation, which is the turbulence. But you see, I could put this phrase here: unstable solids break down in vortices and sound waves generate the turbulence. And this is more or less what comes out from the understanding of the simulation of this system. Well, this is a picture of a real picture. That's the simulation. Without making any adjustment, you see that, and this is the cloud is 3D. We simulate. This is mainly Gross-Pittsburgh type of simulation, and but you see that the main features I preserved, and the main properties as well. And this is an integration. We have this Seeger type of condensate, but you see we make light absorption in one direction. And that observation projects everything in the plane. So this is also the projection of the simulation. And we believe we don't lose a lot by doing that. And of course, when you're doing simulation, you can picture your system at any moment. So you can see all the things going on and the defects you create migrating and not being well distributed. But as the time goes and reacting goes on, there is a distribution around the cloud for everything that we believe we have. There are many observations we made. One of them is that opposite to a non-perturbed condensate, that there is an inverse ratio during the expansion. In this case, there is no inversion ratio. There is a self-similar expansion, and we understand, even Chris Foote showed the retardation of the inversion ratio during the expansion when vortices were present. So the presence of energy in rotation already retarded the inversion ratio. But since we have things for all direction, you may imagine that the system really do not invert. And this is something that we observe, and we rely in time of flight. So we had to justify that most of the energy of the system is in the kinetic introduced by the rotation. Otherwise, time of flight will not really represent what we want to measure by time of flight, which is the momentum distribution. Okay, well, this is a picture. As you see, the cloud expanding, the turbulent cloud, very short moments, you see nothing, you don't have a resolution. But as that grows, you start to see the defect. You can make average and subtraction, and then you're going to see the distribution of defects. And already pointing out to you, oh, my time is over, no? Oh, thank you, Randy. It's very good to be a friend of the chair of this session. But as you can see, there are moments that the defects are not uniformly distributed, because people claim that we should always have isotropy when you have turbulence. I don't think it's true. Maybe this is a consequence of the evolution in your system that may take some time. But at the end, you see all the perturbation going on and distributed. We are trying now to characterize this distribution to the texture. Well, one of the most important things to do is to measure the spectrum, the energy spectrum. So we want to know how, in what scale, what momentum class the energy is distributed. And we do that in two different ways. One is by simple momentum distribution, and assuming that we have theoretical simulations that shows that's very reasonable, that this kinetic dominates. So the kinetic energy in each class is the momentum distribution times chi square. This is one way of calculating, obtaining the energy spectrum, measuring the momentum distribution. Another way is by power spectrum, because after all, the energy may be in the fluctuations of the momentum, and therefore by using theorems that are well known, and by looking the correlation between the fluctuations, you can do the Fourier transform and you can get the spectrum. And we do in both ways. When we do time of flight, right, we always do time of flight anyway, but when we do directly measurement of the momentum distribution by time of flight, we do a time of flight or many different times of flight, and we investigate how many atoms is in a class of momentum. And by knowing this, how many atoms is in each momentum, we can have the momentum distribution. Of course, we are projecting, then we have to make some considerations of distribution and symmetry to be able to recover the 3D. And this is what we call Abel transformation. And we do that since the very beginning of our characterization of the sample. Well, normally what we observe is when you have a few vortices, you see things evolving, but not that much. But when you reach the turbulence, you see an evolution with the development in some class of momentum, which is not very big. I don't have a big sample, so I cannot have a momentum going from nothing to infinite. I have a range of momentum that's basically the inverse of the size of my cloud to the inverse of the size of the perturbation, which is the healing length, basically. And well, we've seen this evidence since 2014, which is the presence of a power law. And the power law presence on the momentum distribution, following Kolmogorov type of arguments, it is evidence of the existence of the cascade. And the power of this power law dependence somehow should characterize the type of turbulence you do, and many theoreticians dedicate themselves to calculate in many situations what is the power law that you find in this cascade. Okay, so of course this is the momentum distribution, but the power law is a little different. You have to take many shots, remove the average, end with the fluctuations, and then doing the correlation and the Fourier transform, and you end also with the evolution of the cloud. I can guarantee to you that this one I put in here, but this is not a range that our approximations are fully valid for the analysis of the momentum. Is not a sample that's kinetic dominated, and we assume that. But at the end, you see the evolution. This is the energy spectrum obtained as a function of different amplitudes. And you can see that after some amplitude, okay, this is dead. Oh no, oh, am I pressing the wrong button? As you can see, I'm gonna save the battery to change the slides, and you take your imagination now. And you see that after some amplitude of excitation for a fixed time of excitation, you see the deformation of the power spectrum and the appearance of this power law range. And both methods give us, when the turbulence is starting to develop and progress, we both see, we get the same result. And we have a momentum distribution that is basically characterized by energy that goes with k to the minus 1, which means a momentum distribution of k to the minus 3. We don't find any minus 530s or anything like Kolmogorov, but that was not expected to have anyway. So this is how a good momentum distribution looks like. We have an isotropy on the shape of the cloud, but the main features are there independent on the direction you look. But just having different range of momentum, because of course, wherever the cloud is shorter, you have less momentum in that direction to analyze than in the others where it's long. This is the simulation. And this is the experiment, less noisy because we do average of many shots. And that's the single shot of the simulation. And I would say that the main features are here, and the development of the turbulence and everything. And with the help of the people, we were able to construct and measure the energy flux. You know, the time variation of the energy spectrum is related to the energy flux. How many really momentum or energy, you choose what you want, are passing from one class of momentum to the next and to the next. And then you can work out the equations, you know, those are like continuity equations, and with the presence of injection of energy or dissipation. And normally we inject energy and then we wait, we see the evolution when we stop the injection anyway. And we are able to come up with a final expression that shows that the flux is the time variation of the integral of the energy spectrum in some range. And once I have that, well, this is, by the way, is well known from the turbulent community. We just apply here, and basically what we're doing is measuring for some momentum class, how is the flux of energy passing to that frontier. And when we do that, well, this is a paper that was pretty much conducted by Lucas and myself with some students, and we were able to really, from the energy spectrum, show that we have, you know, the time evolution of the energy spectrum, where I apologize by my pointer. Where is this made? Oh, maybe in the United States. Have to buy one from China, will work. Okay, so by looking to on the right, you see the evolution of the energy spectrum, and by integrating and taking the time derivative, you're gonna see that there is intervals of momentum on the integration and time variation where this gets in a steady state and don't vary anymore. And that's exactly the interval where the inertial range appears, and that's where the energy is flowing between the scales without the dissipation, preserving the flux of energy moving on that momentum classes. And we do that in different ways, and we were able to identify quite well. It is a short range, but we obtain the power law, and we show that energy is flowing in that range without dissipation, which characterize the inertial range. Well, I know that Eddie Nielsen is here. He doesn't like my entropy, but he has a better one in the paper. Then we start to characterize in different way, density correlation, entropy, and we are able to measure the entropy on the right. Don't look in the left, so Eddie Nielsen is going to get nervous. Look in the right, and you're gonna see the evolution of the entropy. By looking in the momentum class, you can see all these fluctuations and everything, and build up entropy for the cloud. And this is being published in this paper that's called Entropy. And you see the evolution after reaching the amplitude where turbulence is established. You see the evolution of the entropy with the time of holding the sample in your trap, which means reactions are going on and you are distributing the disorder on the sample. Well, there is another way to characterize, is by calculating not the time variation of the energy spectrum, but the length where the energy is more concentrated, by doing that integral of the energy spectrum. So you more or less will tell what is the characteristic size scale, dimensional scale, where the energy is concentrating. Then, of course, this should be going down, and this is called the integral scale length. And we have also measured that and characterized the sample by looking. My idea was, when this extrapolated to very tiny is where the turbulence is starting to decay. You reach the minimum, but by some reason we did not manage it. It takes too long than what we thought for this to decay, where the turbulence will be dissipated. And of course, in that expression of the variation, we imagine this, and L0 should be independent on the amplitude, because that tells you the scale where the energy is located. And for sure, independent on the amplitude of excitation, L0 does not vary very much, but T0, that's depending on the amplitude, because it's the driving force for the reaction, for the energy to flow to the smaller scales. Okay, now I want to apply this, and I wanted to concentrate myself on the Anderson localization. I still did not reach consensus within the group, so I cannot really speak too much about. But speckle of matter and universality we did. So we're going to see how we use a cloud. And the first thing is let this cloud expand. When this cloud is expanding, it should not be like a thermal cloud expanding. It should be like a quantum cloud expansion, but it's not a normal quantum cloud. It's a quantum cloud with random perturbation of amplitude and phases. And this is exactly like the propagation of a speckle, laser speckle field propagating. You have domains, and the propagation is not given only by the normal diffraction, but is given by the presence of a correlation length as well. So a normal cloud has this behavior, as you can see on red. There is an inversion ratio. A thermal cloud reaches 1. A turbulent cloud stays the same. I always like to say that when I am in the United States, I say, imagine a Mickey Mouse balloon, and I'm going to explode the balloon. And if it inside is a normal gas, very soon you don't know that was a Mickey Mouse red, because you're going to have a uniform expansion. If it is a quantum gas, superfluid, if you are smart enough and if you study well in your undergraduate, you're going to see that whatever was more squeezed will expand more, and then you can more or less figure out. But if it is a turbulent cloud, you don't need to do anything. You're going to see a big Mickey Mouse expanding all the time, at least for some range of propagation. And this can be well explained, and the best way to explain is rely on the ideas of Hussein, that said, well, and some other people, there are more people here, and we compare the propagation of a speckle of light field. You produce a laser, it's like a condensate, but now you produce a speckle, you produce interference in a rough surface, random, and then you have a very beautiful pattern of random fluctuations, random amplitudes and phases, and that propagate in a very peculiar way. And then that's what we did. And then, of course, the only thing you have to know that's very important is in a speckle field, in a normal coherent field propagating, the dispersion is the lambda divided by the size. But in a speckle field, is lambda divided by Li, and Li is the correlation length, which is basically the size of the domains. And this is how it looks like. And then when you compare the expansion of a normal back with a turbulent back, it matches very well with the optical beam propagating, having a speckle, and should not be different. Those are waves propagating with the introduction of. And why is this interesting? Well, this is interesting because an optical field, intensity correlation, matter field, density correlation, and you can do both, and you see that, oh boy, you cannot say who is, because the same behavior of the propagation of the two waves. And we have a good explanation for that because of the domains. And basically what's important is here is, I think is one of the first production of speckle field of matter waves, which is the turbulent cloud in expansion. And this is merging quantum turbulence with statistical atom optics, which I think is I know that some people are already mentioning the paper in that sense. That's why I put here. And but the propagation of matter wave is still, we don't have a lot of groups around the world, and we have some groups in interference, and those groups may evolve to these statistical atom optics. And of course, it's a nice demonstration of speckle of matter waves. And well, we have a few papers on that topic. Now, by doing this and by looking to the turbulence, we find out that when we reach turbulence, we also reach a tail of the distribution. We don't have a zero temperature, right? We're never going to have a fully zero temperature. We have low temperature, and we always have a thermal cloud. And by looking to the thermal cloud, normally is a good thermometry for us. And we see it normally is a Gaussian, we fit the Gaussian, and we have a kind of thermometry. But here, when we reach turbulence, we go from Gaussian to exponential, as you can see. And when you have exponential, transition from exponential, from Gaussian to exponential, that means many, many things. One of the things that means is that, oh, this is a non-thermal state. If it is a non-thermal state, well, you can look for properties related to non-thermal states, trying to evolve to a thermalization. And also, well, we investigated this just for you to know. We are looking to the very, very tail, you know, the a few percent atoms that are expanding very fast on the thermal cloud that's surrounding the condensate. And we characterize this in many ways, with amplitude, with fraction of condensate, everything. And of course, to have this transition, we need to have the condensate well perturbed. And I cannot speak a lot, but I believe that one of the possibilities is that the thermal atoms are scattering from the turbulent cloud, and this is like a random potential for the thermal atoms, and that's a kind of Anderson localization. The thing is, I don't produce the random potential using the speckle of light field that Alan Aspect and Inguscio use it in those papers, but I'm using the cloud, the turbulent cloud itself. But this, we don't have consensus yet on the team, so we cannot publish yet, or even try. But this is my idea, is that we have this high momentum scattering from the core and producing a kind of localization. Well, let me jump into this. But what is real is you have a non-thermal state. If you have a non-thermal state during the evolution, it is possible that you have presence of non-thermal fixed points, which are points of metastability, where for some reason the system evolves in a way that compensates variation of amplitude on the momentum classes or energy class with rescaling of momentum. And so we went there to look for this, and this is being published in this paper that's just a few months old. And in that case, all your evolution depends on two exponents, because you rescale. Well, this is also something that evolves from the equilibrium, the renormalization in equilibrium, where people look in different magnification of some scaling, and then that compensate the others and things like this. That is a long story. This is been going on for decades on non-equilibrium quantum system, right? Pre-thermalization and all that. And in those cases, I apologize. I know that there's some theoreticians in the room are even better to explain all the details. But mainly, if you are around, if you have a non-equilibrium and you are around one of those non-fixed thermal points, the system evolves in a well-predicted way. So when you scale the amplitude, that's compensated by scaling the scale of the momentum. And therefore, you have a universal curve, which means that things are changing, but following a universal curve. Everybody asks, what is this curve? Well, that's not the point at the moment. The moment is to say that there is a universal behavior here. And everything is determined by alpha and beta exponents. And of course, in the future, we would like to know, because if you want to know what class of universality is this, it's better to determine this function and see some characteristics of this function. Alpha can be positive or negative. In your case, it will be negative, because we see flux of particles going from low to high momentum. That's our evolution. There are many papers that came recently where studying different basically in quenching. We are doing the turbulent cloud, and you see the momentum, and then you renormalize everything. Everything gets into a universal curve, in a single curve with some exponent. And then those are the evolution of our momentum distribution. And then when you do the rescaling, and that happens in some range of momentum and some range of time. There is a window of time, 5 minutes, okay. And we were able to determine the better coefficients for our case. and it's a minus 0.05 and minus 0.2. Of course, Lucas did a wonderful analysis with variances, and there are, of course, error on those, but they are within the expected, because I'm going to show to you that there are some links between alpha and beta, and we could measure this in different ways. And we find out, of course, I mean, there are some global conservations relations that has to be preserved. Energy has to evolve in some way with the time in the range that you are analyzing, and number has to be conserved. And this is all fulfilled for us. And alpha and beta is related to the dimension. And we were able to really do very good work in seeing the evolution. And of course, we have a 3D system, but we are projecting. And again, there is a very nice analysis here that Lucas and collaborators did, showing out that we don't lose the main characteristic of scalability by doing this detection procedure. And in fact, the alpha and beta we measure has to understand that we mix some high momentum with low momentum. But if the scalability is there, we can get, doesn't matter if we project in 2 or 1 dimension. If we integrate everything, we're still gonna have a kind of universality evolution. Okay, and this is in this paper and in the archive. And I think we were able to prove that you have, during the evolution of the turbulent cloud, this kind of scalability in many different ranges. Now we are amplifying this, and I don't have time, but we have we are constructing a very nice way of looking to all of this, and that we can justify much more than what being observed. And of course, we're still interested in other systems. Oh, this may be in many systems that's in non-equilibrium. And this is a nice experiment that we did in the laboratory of Randy, and we hope to continue, which we see granulation of the condensate as a consequence of perturbation of the interaction. And we created domains that are quite stable, but of course, they have properties. And I think this is a non-equilibrium system that evolves very slowly. And maybe one of the things that are hanging is because there are some important quantum interference taking place that do not allow them to recombine. And Randy agrees, we're gonna go on. This goes beyond the main field. And I think it will be a nice 1D system to study equivalence to what we're doing. And then I apologize, we don't have more time, but there is ways to producing turbulence by letting giant vortices to decay. And this is an experiment of Gustavo Teles, already published. I keep the archive, I don't know, all the transparency, but it's been published. And I don't know if I can show you some simulation, but my time is over, right? A few minutes. This is 2 vortices decay, and 2 vortices of the same sign. The system became very well organized, but if we go, this is exactly equivalent. This is a n equals 4 vorticity, 4h divided by m of angular momentum, and this is a real picture in the lab. When the vortices decay, you can see the 4 little vortices they're evolving, but this is a simulation of 2 vortices with opposite sign decaying, and that's going to evolve to a turbulent system. And maybe that's another way of doing a more clear evolution of those things, but we are working on that. And of course, Michele, a graduate student in the lab, is trying to characterize how the things evolve. I call texture, but I know that we already disagree in many things, is how the perturbation distribute in the sample. And we already trying to find out how that goes. And we also try to understand how we are exciting by doing all kinds of tricks. One of them is separating the excitation. you know, we put one little excitation here, another little here, combine it in time, they produce turbulence. But if I start to separate, I will try to understand how my excitation is making my system to evolve, keeping coherence and everything. This is exactly like two separate zones that was introduced by Norman Ramsey to excite atoms and everything. That's the fundamental of atomic clocks. Now we are applying and we see the interference when we're dealing with collective modes and everything. And just to honor the other student, at this, we are trying to look alternative ways with effective temperature to look the evolution of the turbulence. And there are a few review papers. And normally you don't you want to see the overall picture. So you can look to the review papers. And if you like the theme, if you like nonlinear, if you like non-equilibrium, there is a special issue of quantum science on non-equilibrium, and you are welcome to submit your paper. November is not, was. Now the new date is July 2023, and we got very good contributions already. Thank you very much.
All right, thank you, Vanderlei. We have plenty of time for questions. Yeah, Jeremy, Julian. Yeah, let me see if I can get up there.
Right. Thank you for the very nice presentation. You made this analogy between a laser and a BEC, and then you said the turbulent BEC is like a
Speckle of laser field.
Yeah, exactly. An incoherent, spatially incoherent system.
No, locally coherent. They have domains of coherence.
Yeah, my question is a little bit, so what G2 function would you expect there? Would you expect bunching or anti-bunching? And what is the nature of the
Yeah, I think we expect anti-bunching, yes.
Due to vortices being present.
Well, I think it's because of this disorder there is putting in tiny domains that start to separate each other much more. But I cannot really elaborate too much the answer for you. Okay. They are very similar, but maybe we should think a little harder in what's expected, right? Only being similar. Yeah.
If you would expect anti-bunching, that would be also a very nice indication for the quantum behavior, right?
Yeah, well, of the domains, yes. Yeah, that's why.
Thank you.
Hi, Vanderlei, very nice talk. In the early sort of phase diagram classification with your granulation that you found, and you're exciting a lot, could that be a non-equilibrium state that just doesn't decay and associated to non-thermal fixed points, or is it more likely that you're just heating too much?
Well, I don't know, Nick. It could be what you're saying. It could be that this is in fact, at the moment, we are almost convinced that you may have not one non-thermal fixed point. You may have a sequence that hang the system up, preventing the system to decay in a fast way. Yeah.
Okay.
But I, you know, that's a nice idea, and of course this comes up, but we did not investigate the granulation state. We are in the turbulent state at the moment.
Thank you, Vanderlei. That was a great talk. You showed a picture maybe early on comparing a theory and experiment of a cloud that had gone through turbulence, and you took slices and you saw that they were the same. The experiments seem to have much finer, much faster oscillation.
No, it's because in the experiment, we average many shots, and in the theory, they came with single one.
Ah, thank you.
That's it's a you know, of course. I mean, if they do the average in the theory, they're gonna see a smooth curve as well. But this is the reason. You the referee of the paper, that was the same question.
Thank you for the nice talk, but I have two questions. How do you generate a multi-charge vortex in the laboratory?
Oh,
This one.
well, there are many ways, but you have another one. Let's.
Another question is you talked about Anderson localization. Is it in one dimension or more, 2, 3 dimensions? And what localizes the system?
Fine. First question is easier. It's concerning how you produce a giant vortex. You can produce by spinning a lot of laser, or you can do what we call phase imprinting. By changing the magnetic field, you make the atoms to visit the different states, and that evolves in time in a different way. So it's like introducing a 8-pi phase on your system, and an 8-pi phase around the center is like, it's exactly a vortex of charge 4. This is called phase imprinting. Is something that is more or less well established, the way to do, and then you produce a giant vortex and then that decay. Now, the second question, which is related to the Anderson localization. You see, my idea is that this is a 3D system, that we have this random, and then I have these atoms with our waves, right? Scattering from the center, they are interacting with the center, and that may produce a localization. It's 3D. The sample is a 3D sample.
Self-localization, you are not doing anything, no potential from outside.
Say again, Adhikari.
No trap. This is self-localization.
Oh, yeah, no. You see, it's like you turn off the trap, and then you have this random, you know, the cloud with the big variation of amplitude looks like a random potential for those thermal atoms that are interacting and expanding and propagating. And that will modify the overall behavior. But I'm not surprised if you think is still too, because my group thinks the same. We don't have enough evidences for going for, but maybe having a random core, and that may be a way to producing. But that's why I said is an idea, but not well concretized yet, because my people say, well, we need much more to say that. But you know, you like to say, you say, and then, but there is no confirmation or anything that we've seen. This is just an idea.
So I get the last question as chair. So is there do you ensure that there's conservation of energy when you extract the power law, using the power law method to extract the momentum distribution, or measuring it directly? So do those both agree that the energy is the same?
Yeah, you have to understand, Randy, that we make the excitation and we remove any external input of energy in the system, and we let the system there with whatever excitations we put. And then I don't think the energy is going anywhere besides the internal distribution.
Is the total energy a fitted parameter, or do you extract it from the data?
No, we extract from the data the total energy. That's why we analyze the fluctuation. We do the correlation, and then we do the Fourier transform, and that's how you get.
And they agree, both methods?
Yeah, both methods agree in the range where the sample is turbulent. Where the sample is not turbulent, I think neither method works so well, because the origin of the momentum is not what we say. The origin of the momentum is interactions and many other things that are there. So in the range that we see the turbulence, is in the range of excitation, where we are characterizing, they both agree. And of course, we need to do Bragg scattering. But even people from Cambridge that are doing turbulence in a box type trap, they are not doing Bragg anymore. They did Bragg, they did the time of flight, and they realize it's the same, so they use time of flight, which is simpler, and you get a more broad range of momentum, because you get the whole sample from UV to infrared.
Okay, all right, great. Let's thank Vanderlei again. The next speaker is Patricia Castillo, and Patricia will discuss town solitons.
gas. And before starting, oops, it's not passing. Yeah, okay. So I want really to thank the organization committee that made it possible for me to be here, because they allow me to bring my young daughter. So here is she, Elisa, in Uncle's Vander's van. So we came from São Carlos all together. So she's happy and smiling later. So this is the beginning of the trip. So everything was fine. Later she screamed a lot, but was okay. So she's here, and my oldest daughter. Oh, so it's not passing. This, yeah, okay. Was at the swimming pool at the time, so nice. Both of them are happy. So thank you very much, especially Gamal, that made this possible. Okay, so let's go to physics. So for my presentation. So as I said, the title is Town Soliton in a Planar Bose Gas. And pretty much my presentation has two main topics, if we want to think like this. So there is a planar. Okay, so the part of the planar Bose gas and the part of the soliton. So I'll try to do a very brief. So are you passing or myself? Because it's kind of weird. I'm not having the control on the slides. What is? Vocês estão passando ou sou eu que estou passando? Porque não está funcionando aqui direito. Sou eu que estou passando? Não, né? Ah, mas então não está funcionando isso aqui? Tá, entendi. Bom. Pode ser, porque senão aí fica meio confuso. Tá indo e vindo? Tá bom. Ok, obrigada. So sorry about that. This is not working. They are passing the slides, so I'm trying to synchronize with them. Sorry. Okay, so my presentation has these two parts, let's say. So one is the planar Bose gas. So what do we understand by planar Bose gas? We will be talking about two-dimensional or 2D Bose gases, okay? So these gases, just to give a very brief introduction, they are produced by 3D gases that are strongly confined in one direction of space. And this confinement is usually done by a harmonic confinement, such that the atoms occupy the lowest energy state of the system. And if we reach that condition written over there, below the harmonic confinement written, we are in the regime that we say the gas is kinetically 2D. So all the dynamics of the system happens in the plane in 2 dimensions, and we can say that the gas is effectively a 2D gas. Okay, so next slide. And then in this situation, if we are in the weakly interacting regime, we can use a classical field phi to describe the system, and this classical field will be governed by a 2D Gross-Ptaevsky equation that I wrote here. Okay, so then the interaction between atoms happens as a contact interaction, and the coupling constant that governs this interaction is given by this G tilde, which is a dimension. Next slide, please. Which is a dimensionalist parameter. So there is no length scale associated with the interactions in a 2D Bose gas. And this next slide. So this is something interesting, because then in this case, the system will have the property of having a scaling variant system. And when we say about scaling variant system, we are saying that this system, so the action that describes the system, is invariant over a dilation transformation given by these two relations for position and time. And from this characteristic, we have many properties that arise on these systems. So we have the university of the equation of state that is describing the system. We can see the appearance of 2-dimensional breathers, as we saw on this publication I listed over there. We have also an undamped oscillation of the breathing mode and other effects that emerge from the fact that the system is scaling variant. So this is a very brief summary of the characteristics of a 2-dimensional Bose gas in this regime. And then next slide, please. We can go to the second part of my title of my presentation, that is the soliton. So of course, I'm speaking to a very expert audience here. Probably most of you know what is soliton, but I want to give an idea for the people that are not really used to soliton or solitary waves. So we can describe these objects as being a localized wave packet which propagates without deforming itself due to the compensation of a dispersive medium and a nonlinear effect present in the medium. So for the youngest one, they can think, okay, these objects are quite weird and exotic, but actually this is not the case. So next slide. So the first observation of a soliton was done in water, so in the Edinburgh Channel by John Scott Russell, and he saw a bump of water in water that was propagating along this channel without deforming itself. So here there is an image of the reconstruction of such a soliton, and you can see that over there. So this part here, this bump of water is propagating along the channel, and this is the soliton, like the one observed by Russell, okay? And this is relevant. So he described this soliton as this sentence here, so a round and well-defined heap of water, which continue its course along the channel, apparently without change of form or diminution of speed, okay? So it was propagating pretty much as it started. And this is relevant in many, many areas, in math, in chemistry, and in physics, especially in photonics, when we think about a wave packet of light propagating in an optical fiber. Okay, but in ultra-cold gases, what can we say about solitons? So they are vastly observed during the years, and especially in quasi-1D geometries. This will become clear in the next slide, why this is so. But we have the production of bright solitons produced after interaction quench, from which we quench the interactions from the repulsive side to the attractive side. So we have here results from Christoph Salomon's group, and here from Randall Hewlett. We have later there is another paper, very nice paper from Hewlett on this that I will show to you. And they were also produced by phasing printed methods, in which they could produce a dark soliton here. So it's a dip on the density of the gas that was also propagating along the cloud. And more recently, magnetic solitons producing two-component, almost 1D systems by the group of Ferrari in Trento. Okay, so then we can take a look on their energy functional in D dimensions that describe this soliton. So this energy functional will be given by this expression here, in which we have the dispersive term that is given by kinetic energy, here in this first term, and the contracting effect of the media, that is going to be a nonlinear effect, that will be given by this second term when G is negative, okay? So this is a generic equation that is applied to many, many branches of physics, as is written here. And if we look now to this equation in order to do a dimensional analysis of it, we can think about a wave packet, psi, that is going to have a characteristic length given by L. And this length, the dependence on this length will be proportional to L in the power of D here, that is the dimension of the system. If we do this and we replace this on this equation above here, we end up with the energy being proportional to this relation. So we have two terms that compete themselves, and the soliton appears when we balance these two terms, okay? So there is a crucial role of dimensionality in the system, because the term that the second terms has a dependence on dimensionality. So then if we continue analyzing it, okay, so we can go further on this dimensional analysis and plot the energy as a function of L here. And we see that in 1 dimensions, we have a minimum, okay? That means that we can have a stable soliton for a given energy here, and with a characteristic size that will depend on the number of atoms, the number of particles actually, and this constant G. So this, so here is the other paper I mentioned by Hewlett, in which they do also an interaction quench to the attractive side, and they go to two different values. So you see that the formation of a soliton train, so these many bubbles that appear in this 1D gas, and the size of these bubbles is related to A, that is the scattering length of the system, that is here in this constant G. So we see this clear dependence on the L, which is the size of the soliton. Okay, now if we go to a 3D system, so look first at the at the blue curve, we see that the behavior of the energy as a function of L has a maximum. So this means that a soliton in 3 dimensions is unstable, dynamically unstable. You can produce, but it will be destroyed by any fluctuations of your system. If you now think about this dashed red line, this is the case when we consider the harmonic trap that is present in most of the systems. So in this case, you still have a local maximum, but you also have a local minimum. And that's why some people can also see a more stable soliton in 3 dimensions because of this local minimum that appears on this L minimum here. But then the case we are interested in is the case of a 2-dimensional Bose gas. And if the dimensionality of our system is 2D, we see that the 2 terms, they behave equally. We have both proportional to L to the power of -2. And it can exist a stationary solution for this case, but it only exists for energy equals 0. That is this dashed gray line here. And then this will exist whatever the size of L that is the size of the soliton. And this will happen just for specific values of this coupling constant G and the number of atoms N, okay? So this is, so we can now rewrite the nonlinear Schrödinger equation for the soliton in 2 dimensions that is written here. And we can try to find this stationary solution, the stationary solution for it. So this is exactly what was proposed by Chow, Garmidi, and Townes in 1964, that today we refer to as Townes soliton. So it will be a radially symmetric and nodeless solution of this nonlinear Schrödinger equation in 2D, which will exhibit a quasi-exponential tail here, okay? And this will will exist for a specific value of this factor G tilde n that is equals to -5.85 with many other numbers after this 5. And the energy of the system is going to be 0, and the chemical potential will be a negative. Okay, so if we manage to produce this kind of soliton in a 2D system, this expression is pretty much the Gross-Ptolemy equation I showed to you at the very beginning when I was introducing the 2D gas. And this equation will also have scale invariance, okay? It's the same type of equation. So how scale invariance will appear on the system now? It will appear in the following way. So if we find a particular solution for the soliton on this system, given by psi of R, we can build a family of solutions. We can think about many other types of solitons that will have the same shape, but with different sizes, that will be given by this relation here, and in which we modify the chemical potential by this other relation. okay? So this is, again, a signal of not having any particular length scale associated with the Townes soliton. So there is no characteristic length for it to appear. It only depends on this relation on G tilde n, okay? Okay, but then it will be unstable with respect to any change of n. So if you create a soliton with a given atom number, for example, you lose the atom number, you lose the soliton properties, it will start to spread, okay? Good. So in 2021, two groups have seen this Townes soliton in 2D gases. So the first one is the group in Purdue in China. And what they did was an interaction quench, as people was used to do in two-dimensional systems. And they saw their system that was before the quench an almost 2D system, becoming a quasi 2D and breaking into small bubbles here. So these bubbles, so these are single shot images. And they, what they did is to get the density profile of each of these bubbles and plot on this graph here. So if they do so, they can rescale all these density profiles to a single density profile here, proving that these systems are really scaling invariant. We can do a simple transformation of this, each of these density profiles and recover a universal curve for it, okay? And there is also our result in Paris that was done with a two-component Bose gas of rubidium atoms. And the difference of our approach is that we do a deterministic preparation of this Townes soliton. Instead of quenching and seeing how the cloud breaks into solitons, we do a deterministic preparation of this by imprinting an arbitrary spin distribution in a bath of atoms in species 1 to a localized bubble in species 2. So here is pretty much the images that we got. So this dashed circle here is our bath, so in species 1, and here is the bubble we imprint in species 2. Okay, in this situation, and if we transfer just a small tiny fraction of atoms to the other species here in the center, we are in what we call weak depletion regime. And in this case, this species 2 can be described by effective single component Gross-Ptaevsky equation with attractive interactions. So it's exactly the case that it suits a Townes soliton, and I will show this to you, okay? Okay, so this is the outlook of my talk. First, I will give to you how we construct this effective single component equation for species 2 in our case. Then I will give also this reference is wrong. I recycle this slide, sorry. So these references are wrong, don't think about them. But then I will show the experimental setup of producing such a soliton, and then I will show you the results. If I have time, this will be the part 1 of my talk, and in part 2, I will talk just a little bit of what we are going to do in São Carlos in a new experiment to produce tunable 2D Bose gases. Okay, so nice. So as I said, we are in 2 dimensions, and we have two hyperfine states of rubidium atoms that we are going to work with. And in 2 dimensions, we can write the 2D Gross-Ptaevsky equation as this simple form here, in which I just normalize the parameters, dividing it by h bar and m, okay? Okay, so if now we have two components in this gas, what we have is a system of coupled Gross-Ptaevsky equations, one for species 1 and the other one for species 2, with a coupling term that will depend on the interspecies interactions and the density of the other species we are dealing with. Nice. And if we think about the physics of bulk mixture, what we will have is the appearance of 2 different miscibility regimes that will emerge from the competition of the inter and interspecies interactions in the system. So the system can be miscible if I define this delta comma parameter here, and this delta parameter is larger than 1. So it will form a uniform mixture, or it can be immiscible if this delta comma parameter is smaller than 1. And then the system will remain phase separated in some way, side by side, one in the center, the other one surrounding it, it depends. Okay? So this is a bulk picture of what happens in the case of a mixture. In our case, for this experiment of the Townley soliton, we are interested in a localized wave function for species 2 immersed in a bath of species 1. So here is my bath of species 1 that is a bath with a hole in the middle. So you see here is the scale of density. So this hole is just a tiny fraction of hole because I transfer this population that is missing to state 2. Okay. So if I do a plot of the density, I see a small depletion in the center of species 1, while I have this localized bubble for species 2. So this is our is the picture of our system. And we can do some assumptions. So we have this strong localized wave function for species 2. And then far from the center, the species 1 remain unperturbed. So it's what we see here. The density of species 1 doesn't change far from the center, okay? All the interactions in our system, intra and interspecies, they are very similar. So this is true for rubidium 87 atoms. And I have these two relations being smaller than 1. This will simplify a lot our couple Gross-Ptolemaev equations. And I can think that the total density of the system is constant. So any1 plus any2 is constant to any infinity, plus a small fluctuation that I will call delta n here. So this delta n will be much smaller than this n infinity, that will be the density here far from the center. Okay, so I can write the equation of states that, the wave function that describes species 1 approximately as this relation here, where I subtract the density of species 2. So now if I go back to the couple Gross-Ptolemaev equation and I change this relation into the equation for species 1, I get an expression just for delta n, okay? So which is the fluctuation on the density. And then this equation here for delta n can be inserted into the Gross-Ptolemaev equation for species 2. If we do so, we end up with, so I summarized very fast the math, but it's simple, it's just math, it's just put there and you get this equation here. So this is the final equation that we have for species 2, where I neglect all the 2, so it's mu2, phi2, I remove all these 2 indices to simplify the notation. So this is an effective single component equation. And we have 4 terms. We can take a look on these terms. So this term is a constant. I can sum it over the chemical potential over there, so it can disappear. I account it on my chemical potential. And there is this other term here that's a bit more complicated. But if we are in the weak depletion regime, where this n, that is the density of the second species now, is much smaller than n infinity, that is the density of species 1 here in far away from the center, this can go out. And in the end, I get an expression that is pretty much the Gross-Ptolemaev equation for a single component that we are used to, with a kinetic term and an interaction term. Okay? And this G tilde A that I put here is this parameter here. Okay? Good. So this is exactly the 2D nonlinear Schrödinger equation that I also discussed in the case of having a soliton in 2D. So I will have the possibility of having a Townley soliton on this system, which will exist for this parameter here, G tilde multiplied by n equals to 5.85. Good. So in the experiment, how do we do? I said we work with rubidium with 7 atoms, and we have the bath in the ground state F equals 1, and the localized bubble in F state equals 2. And here are the relevant scattering length values. Okay, so now let's go to the experiment. How do we do this in the experiment? So in order to produce a two-dimensional Bose gas, as I said to you before, we are going to strongly compress a 3D gas in one direction of space. So this has to be very cold for this gas to be compressed in a single layer of very tiny layer. So we have to do everything up to the production of a 3D Bose-Einstein condensate. That is depicted here in this figure by this ball. So next, what we do is we load this 3D Bose-Einstein condensate into a vertical optical lattice with a spacing of about 6 micrometers. And then we confine these atoms in the plane with a digital micrometer device, a DMD, that I will not give too much in details here. I think the audience is well aware of how the DMD works. So it's an array of micrometers that we can control individually, each one of them, creating what we call a box-like potential in 2 dimensions. So this will allow us to have a uniform density of our cloud. And then once they are in this trap, we can evaporate deep into the degenerate regime. And for example, we can do this very nice star of atoms that I'm showing here just by simply putting this star in our DMD, okay? We can vary this potential as we like, so we have a lot of flexibility on the shapes we produce this 2D cloud. And this is the starting point for our experiment. So then one thing we can ask ourselves is just to know the power of this system is if it's possible to produce any arbitrary 2D cloud. And the answer is yes. We can use what we call gray levels technique applied to our DMD to produce not only uniform, but smoothly varying density profiles on this 2D cloud. And the idea is that if we take an image of our atoms and we expand this image in order to be able to see the pixel of each image, which is about the same size of our optical resolution that we image the DMD, inside this pixel of about 1 micrometer, we have imaged 25 micrometers of the DMD. So we have 25 combinations of on-off, on-off, on-off of the mirrors that will average in this image resolution unity, such that we have 25 intensity of light coming to our atoms. And this, if we combine this with error diffusion procedure to create smooth images with our DMD, we see that we can create a flower with different levels of gray here. That is actually, it is like this because our eyes, they average these micrometers that is set to on, off, on, off, on, off. So here I have only white that is on and black that is off. And our image, our eyes, they average this on, off, and we see this as different levels of gray. So this is what will happen also in the atoms. If you do something like this, we will see something that will have different levels of density in our sample. So nice. So this DMD, we can do perfectly uniform systems. We can vary the density of the system. So super nice. And in practice, in the experiment, what we do is we add a second DMD and do a feedback loop that I will not enter in the detail. But this is nice because, okay, I can create smooth varying density. So I can create here a squared box with a linear varying the density in one direction. I can create a Gaussian density here. I can vary the density of the cloud radially as this image, but I can also improve the homogeneity of my system, taking into account the imperfections of the system. So now I have a very, very uniform bath to start with when producing the townized soliton, when I do all this feedback control. Okay? And then now we have to be able to transfer locally the atoms we want to transfer to the other state to create the bubble. So we can do transfer between different hyperfine states in many different ways, using microwave or radio frequency radiation, or we can use light, for example, a 2-photon Raman transition. This is nice because the atoms will be transferred only where there is light shining on your cloud. It's not something that will transfer all the atoms at once. So if we just shine light in a small fraction of the cloud, it's just there that the atoms will be transferred. So we can address the atomic cloud locally. And it's this what we do. So we use, again, another GMD to perform this transfer. And here we have to use the gray levels technique because we want to imprint a shape on this bubble. So that's why I present to you the gray levels before. So we have to use it here on this GMD in which I shine two laser beams with slightly different frequencies that will do a Raman transition from state 1 to state 2 in my atoms, okay, with no transfer of momentum to the cloud. So I do this by trying to by drawing here a small bubble in the GMD that will transfer then just a small bubble in the center of my cloud, enabling to create this picture that we are interested. So here is how it looks like. So yes, I can create just a small bubble. So the cloud is this whole circle here, but I create just a small bubble with very tiny error or what I wanted to produce. And if we look now to the density distribution of this bubble, I have this profile that is exactly the Towns profile we ask the GMD to produce. So this Towns profile is obtained numerically, solving this the previous Gross-Pitaevsky equation I showed to you before. And we ask the GMD to do this profile, and we get exactly this on the density of the cloud. So we have almost exponential tails, and we have a very good precision on this profile over 2 decades of density here. Okay, so now let's see what we do to really see the soliton. So we have this bubble here being transferred in the bath of atoms in species 1. And this is our Townes condition. So what we do in the experiment is we cannot really change the interaction couplings in rubidium because there is no allowed Feshbach resonance for rubidium-27, but we can change the atom number. So we change the atom number by changing the time duration of the pulse of the Raman transfer. So we can change n, and we can try to probe this relation and see if we see the appearance of a Townes soliton. So what we expect to see, we expect to see a stationary dynamics. So it's a soliton. It will stay there without changing its shape for a long time. Pretty much the time in which I start to lose atoms and I depart the soliton condition. So we expect this not to change with time. So the experimental sequence is pretty simple. We produce the planar Bose gas, the 2D gas. We transfer a fraction with the 2-photon Raman transition here for a variable T Raman. Then we look for the in situ evolution of this bubble in the bath, changing the time t, and then we do an in situ image, in situ absorption image, like this one I'm showing. So this is the experimental sequence. And what do we see? So I'm showing to you the result of 3 different atom numbers here for the same size of the soliton profile we imprint. So all these 3 cases, we imprint what would be the Townes profile for this system, just change the atom number. So it's the same time profile we imprint with the DMD, but we change the duration, so we change the number of atoms we transfer. And here I'm showing the evolution, the density profile evolution for 3 different times, evolution times, so 0.8 milliseconds, 20, and 40. And we see that if we have a small atom number, the density changes and it spreads and the peak density diminishes. If I have a larger number, so here, this red case, we see that actually the peak density increases and the cloud shrinks. So this is an effect that the interaction between 1 and 2 is larger than the interaction of species 2 itself. So it tries to compress when we have a lot of atoms to diminish the energy of the system. But then if we have this particular number here, 720 atoms in the bubble, we see that the profile is pretty much stationary. It doesn't change. And if we get the size of the profile, the width, we see that it's this green curve here. It doesn't change. It's pretty much constant over this whole range of time we are looking. So this is what we say, recognize as the Townes soliton in our system. And we can do a fit of this data, considering the virial theorem for the Gross-Plevsky equation, such that we have this relation for the width of the cloud, which gamma being given by this parameter here when we consider the Townes profile. Okay, so we fit all this data by this relation. And we can now vary the number of atoms as we did here, but we can vary the size of this bubble that we nucleate. And this bubble, if we vary both things and we do the same analysis and plot them, plot gamma versus n in this graph for different sizes and different atom number, we see that all the values pretty much collapse into a single curve. Okay. So here we are saying this gamma is the expansion coefficient of our cloud given by this guy here. And the Townes soliton condition is where this gamma is equal to 0. So where these points cross this dashed line. Okay, so nice. So we can do things that are not soliton with larger atom number or smaller atom number, larger atom number, and the Townes soliton happens exactly when these two lines crosses. And here, since they all follow into the same curve, we clearly see that there is no length scale associated with this Townes soliton as we were predicting looking to the equation. And we can get the experimental number for the formation of this Townes soliton by looking doing a fit to this data and looking where it crosses 0. And we found 790 atoms where the theoretical prediction gives to us 770. So it's they match well within our error bars here. Okay, so this is pretty much what we have seen about the Townes soliton. So here is my conclusion. So we wanted to produce a deterministic Townes soliton in a two-component Bose gas, two-component planar Bose gas. So for doing this, we rely on the weak depletion regime of the bubble we nucleate, such that we can describe the bubble by an effective single-component description of this bubble given by this relation here. And then we could realize this theoretical picture I showed to you by doing a two-photon Raman transfer between states 1 and 2 with the light being modulated by a DMD device in which we use this grid-level technique so that we can imprint any density profile we want, especially the Townes profile. And how do we look to this Townes soliton? We imprint and vary the number and look for a stationary evolution of the shape of the density distribution and especially the RMS size of this distribution. And we could prove in scaling variance for the system by looking at different sizes of this bubble and seeing that they all collapse into a single curve. given by this relation for the expansion coefficients. So of course there are perspectives on this thing. So we can think about what happens if we departure this weak depletion regime. So then we have to add this extra term. I remove that complex term. I remove from the description of the bubble, and then that extra term will break the scale invariance. So we will probably still hold a Towness soliton if we don't do a very big depletion, but the system will not be scale invariant anymore. We can also think about how this Towness bubble talks with quantum droplets. That is something that's very trendy nowadays. So, and there are many experiments and proposals with quantum droplet systems. So people look for how these droplets expand, how they collision between themselves, excitation, so mode excitation, vortices, etc. We can think, what about the Towness soliton? So these are different from the quantum droplets. That is something that happens when we consider beyond mean field interactions to the system. The Towness soliton I presented here is a pure mean field object. But then we can think about which are the similarities with these quantum droplets in terms of all these things we can observe on the systems. So this is something that can be nice. And also we can think about changing the interaction. So we couldn't do this in the system I showed to you because we work with rubidium atoms. But if you work with some other species that you can tune interactions, so what is the play of interactions when we change them very much? So even departuring the quasi 2D regime I said before. So this can also be nice. And you can go to a situation where you will stabilize the Towness with a very few number of particles. So here we need 790 particles for this Towness soliton to be formed. But if we increase interactions, you need much less. So yeah, there is some things that can be interesting on this direction. Okay, so this is the team that produced these results. So the hard work was done by Brice, that was the PhD at the time, but all the rest also contribute to the results I showed to you. Okay, so do we have some time, Randy? So it's very brief. I will not delay the coffee break. I know everyone wanted the coffee break now. So I just want to give you a flavor of what we are going to do in São Carlos. It's not super well defined. I have many things I would like to try, and I'm interested in 2D, but competition is hard. There are very good people doing nice things in 2D. So by the time I built my experiment, I don't know what will be interested at that time. So we have ideas. And we have a proposal, but let's see. I don't know if we will really do this. We will departure from that. I don't know. Okay. So, okay, I'm also as Vanderlei in the Institute of Physics of São Carlos from the University of São Paulo. So in São Carlos, so here are two nice pictures of the campus. So this is the Physics Institute, and here is just a nice place of the campus. But then what about the new experiment in 2D? So now it's pretty much an empty table. Not that empty. We have already a laser that we took from another system that is not going to use this laser anymore. But yeah, it's still pretty much empty. But we have some ideas. So as I mentioned, there are many things I'm interested in 2D. So how the system behaves, the superfluid properties of the system behaves when we increase interactions. Departing the weakly interacting regime is one idea. Efimov physics in 2D, I also like. I also like nonlinear, non-equilibrium stuff, as Vanderlei said. But for the moment, the idea is that we are going to pursue the nucleation of quantum hydrodynamic instabilities in two-dimensional Bose gases. So this is the traced path so far. And for this, we got from Brazilian researchers, they all are used to FAPESP, which is our main funding agency here in São Paulo State. And I got this very nice project. So it's an initial project, PI, that is for young professors to start a career, pretty much. So it gives a nice amount of money, and I just got this at the beginning of the year. So we are going to start, okay? And so the idea is that I will do a system that is very similar to the one I described to you. I use a lattice to confine the atoms in the 2D regime. I will have a DMD to have a very flexible 2D potential to create my quantum gas. And I will also implement the spatially selective spin transfer I showed to you to the Towney soliton. But the difference is that I will now work with potassium atoms. So potassium, I will have so potassium 39 have very nice Feshbach resonances. So I will have the possibility to play with the interactions to study all the phenomena I want to study. Okay? So the idea is try to reach the conditions for the onset of this quantum hydrodynamic instability. And to start with, we will focus on this Rayleigh-Taylor instability that happens when two components, two fluids, sit, for example, side by side. So one species in the bottom, the other species up here, upper, yes. And then I push these two species one against each other. So there is a critical velocity for them to be pushed one against each other, such that they start to develop some modulation on the interface. And this modulation evolves to these mushroom type structures. That is the clear signature of this Rayleigh-Taylor instability. Then I hope that we could look for further time evolutions in which these mushroom structures, they break, and I have the appearance of vortices that emerge from the head of these mushroom structures. And then I can look for the long time dynamics of the system and see how these behave system prior the onset of the instability, and also here at the beginning of the appearance of these patterns evolve to something that is out of equilibrium now in 2D. So yeah, so this is pretty much the first path we are going to pursue. We are going to work with two different hyperfine states of potassium 39, which I can tune the interactions, so I can play with the interactions between the species or the force that I push these two species to see the onset of this instability. And the forces are going to be modeled by the DMD also. So I can, yeah, imprint any type of force I want in any, so I can choose to imprint in one, so one goes against the other, or in both, so they collide pretty much. And then the idea is to map all the phases of this instability. So this is the image of a theoretical proposal here from 2009. So this is not for a 2D, real 2D system. So this is for a pancake BC. But then, yes, so maybe we have some peculiarities of being really in 2D that we will merge, especially at the long time dynamics, I believe. Okay, so is it. So I wanted to thank you all for watching me, and this is my daughter, happy coming to the to the workshop. So thank you.
All right, thank you, Patricia. We have time for questions. Yes.
Olá, Patricia.
Hi.
Thank you so much for this very interesting and inspirational talk. I wish all the best for the new stage of your career. I have a question about the physics of the town solitons. You said when you started your analysis in the introductory part, you said that if you in 2D, if you assume some wave packets with some length, typical length, then you don't have stable landscape for the solitons. But then when I see the picture of your town solitons, I see that it decreases with there's some aperture there, which is related to the healing length somehow now,
Where
in a special profile of the soliton. You said that it's scaling variance, but this is if it's exponential decay, so there is a scale associated to this, no? The healing length or something like that, equivalent.
Yeah, so there is, so this I can change as I want, actually. So the idea is that once so the town is soliton in 2D, any soliton, which in the end, here we are dealing with a town as soliton in 2D. So it's this. So if we look to the energy as a function of this characteristic length here, okay, in 2D, I have no minimum. So the minimum in energy means a stable solution for the action of the system with a wave packet with this characteristic size. Okay. So in 2D, I have no minimum. So the two terms, they compete, but they scale equally with this size. Okay. So the only possible way for me to have a stable soliton in 2D is when I have the energy of the system equals to 0.
Okay.
Okay, so in this case, there is no intrinsic length associated with the town as soliton. I can nucleate a soliton with different sizes. The only thing that matters is this product here. So I can model a soliton with a size that it can have any size, but this has to be satisfied.
This I think I understand. It's just that when you put the plot, right, when you show the profile.
Yeah, but this is a choice that we did. So we did a choice also here. Okay. So the size of the towns, it's something that we decided to do. So it's so I say, okay, we are going to do a with element size of 5.
I see.
10. So this is what we try to do in the very end. So the initial results, we choose a specific size that is a size that is not, so you see the whole size of the cloud, we have to choose something that is small compared to this size. So the standard size we use is about 5 micron, you see, RMS size. But we can change, we can define others. And we did this in the very end to see how scaling variance acts on this system. If the behavior of the wave packet can be rescaled by, yes, so if we see the same universal behavior. So we did this by not rescaling the density as the other group did, but we did by looking at the expansion coefficient. And here we change. So we change, but it's something that we plug. Okay.
All right, thank you. So the product of G times N is the relevant quantity.
Yes.
And that's true in any dimension.
No, it's true in 2D.
So in 1D, you can scale a soliton also by, as long as you keep GN fixed.
But then the size changes, right? So if you change the energy of your system, you have different sizes of the domains, the droplets that appear for the soliton.
We can talk later, but it only depends on the product of G times N. And the size depends on the confinement dimension.
But even on this, on your results, just to clarify now,
yes.
It's my doubt, okay? But here, what I understand from your images, let me go back to this, okay, is that the size of this soliton chain the soliton train and the solitons in the soliton train, they change as a function of the interaction parameter here. So you're changing the energy of your system,
Yeah,
and
but
they naturally form different size of.
yeah, that's true. The n times
Okay, but
A is,
it's in it's in
the-
G.
the
Okay.
n times A is different in those two plots.
Okay. Okay, we can talk
Yeah.
later. So now it's
Right.
my doubt. Okay.
Yes,
But can I ask another thing, Hewlett? So can I just comment on? Okay, so Randy, can I just comment? I think I got it. Because here, so for example, here you have an energy, a quantity for the value n multiplied by g that stabilize your soliton in a specific size. So it's going to be this size here that minimize energy. In my case, it's what I told to him. I have n times g, and I can choose whatever size, and it will be stable. So it will be a soliton. For you? Really? Yeah, no, I understand this, but the characteristic size. Yes, yes. But like if you could have any size here, just matter n times g, you had bubbles that are very small and very big and very small, very big. What you have here is bubbles that have pretty much the same shape, the same size, because this size, okay, it's related to ng by this relation here, but you have only one stable minimum. So all the solitons you create by quenching that you do not imprint, they have the same size because your size is restricted, okay? Because if I do this on my system, is what the guys in Purdue did. They had bubbles with slightly different sizes, okay? And but that respect the product n times g equals to 5.85. And then when they rescale this density, they fall all into a same curve. But there were different sizes of bubbles with the same value of n times g. Okay, but we can talk later. Sorry.
Maybe on a different angle, looking at when you have higher than the critical number, the cloud starts to peak up in density and get smaller. How does that break down, or how does that eventually, if you keep pushing that, what happens to that cloud? Does it collapse? Does it disappear? Does it blow up?
We end up losing atoms by three-body losses, and then this cloud starts to expand again. So this contraction effect is just a result that the intra-species interactions of the bubble is smaller than the inter-species. So then it's energetically favored for the bubble to shrink, but then it shrinks too much. We have three-body losses, we lose atoms, and then it starts to spread.
Thank you. I have one question. The town soliton is stationary but unstable. It's but if you put in a bath, it remains stationary but unstable. But what is the role of the bath?
So here the role of the bath is none. So in the end, I can reduce my system as if I had a single component. So the only effect of the bath is on the interaction parameter, the effective interaction parameter. But the bath itself, at least when I'm in this weak depletion regime, play no role. Instead of changing the interaction coupling, is that just this, okay? But yes, so if you think about the expansion of a bubble, any bubble, a town, a soliton or not, in a bath, in rather different situations, then you have to think of what the bath does on it. Here we can remove this by doing this effective thin component picture. So it's imbued there, but yeah.
The soliton, town soliton is unstable. How much time leaves your town soliton? Because it will collapse after some time. I didn't see the scale of the time it lives.
So it lives quite a long time. in the end, able for experimental parameters. So we could look it to, yeah, 1 second more or less. Oh, 1 second, no, sorry. 60 milliseconds, 100 milliseconds. Yeah, yes. Yeah, so yeah, for now we showed it up to 40 milliseconds, which pretty much doesn't change. So and then we are limited by, so the instability will appear due to atom number fluctuation, which will be atom number loss. So as long as we don't have loss on our system, this will be stable. So here we choose to show up to 40 milliseconds, but I'm sure we saw up to 100 and it was quite nice. It was not still starting to spread to 100 milliseconds. But we are limited by losses on the bubble, losses in the F equals 2 component, which is the one that loses more fast in the end, but okay.
Hi. Oh, last question. Okay. Hi, thank you for the talk. Very nice result. I was wondering about the role of temperature. So how cold is your gas? Is it completely superfluid? And what would you expect if it was hotter? So if you would go close to PKT transition, etc.
So we are very degenerate. So 20 nano-K. So it's pretty much fully degenerate. And we did do some tries with finite temperature, increase the temperature, but then we couldn't see this nice stabilized profile here. Things were spreading much faster. So we saw a faster expansion of it. We tried to play a bit, change the parameters and try to understand. In the end, we didn't find a reasonable model to explain what we were seeing. So that's why we don't put this also in the paper. So this is also a question, actually. Thank you. Thank you. Thank you. Thank you very much. Let's see. Coffee time.
talking about solving turbulence in low-dimensional quantum fluids.
Thank you so much for the introduction. First of all, I would like to acknowledge the organization of this beautiful workshop. It's been a pleasure to see that all the speakers bring a very high level of scientific discussion to this meeting. Also, in particular, I would like to thank Arnaldo for inviting me. The things that I will present here are still under construction. Okay, so we have already some results, but most of these ideas are under development. So probably you should read this solitonic turbulence in low-dimensional quantum fluids, something like towards solitonic turbulence in low-dimensional quantum fluids. Okay, so most of the ideas that I will apply here, that I will describe here, are thought for Bose-Einstein condensates, atomic Bose-Einstein condensates, but I will try to keep the discussion as general as possible. And eventually there are some other platforms that will appear here where this physics could be in principle envisaged. So just wait a few seconds for the people to get in the audience. Thank you. It's okay. So I will start with this motivation, try to give you the glimpse why we should bother about these solitons and soliton vortices, soliton gases in general, and how these, in particular, how the features of multiple soliton interactions are in particular interesting for the analysis of low-dimensional turbulence or quantum turbulence in low-dimensional quantum fluids, especially in what we call the strong turbulence regime. Then I will try to motivate a statistical description of multi-soliton solutions. When you break down the integrability of these systems, then you have to deal with incoherent arrays of solitons. And if you have many solitons, we cannot describe them analytically, let's say, in terms of the mean field description. So what we have to rely on is some statistical procedures. So this is what gives rise to what we call solitonic kinetic theory. Then I will try to go to two-dimensional systems, and especially after this beautiful discussion about the presentation of Patricia, you will already have the motivation for two-dimensional systems, so I don't really have to spend much time explaining why two-dimensional systems are so interesting, because Patricia already did this work, and also with Vanderlei, we explained everything about turbulence, so all the introductory parts will be much easier for me now. I will also, in the same spirit of what I did, or what I will show you briefly on solitonic kinetic theory, I also try to motivate what's happening with kinetic models for vortex gases. And this is really ongoing work and has lots, and I'm very happy to see that this could be very well connected to the work presented by Monica yesterday, when she talked about these many vortices, or when she tried at a certain point increase the number of vortices on top of this sphere. And you see that this dynamics complicates a lot. And that's exactly where kinetic statistical physics could be interesting. And then I will try to some conclusions. So why bothering describe solitons and vortex gases, or why should we talk about this concept in the first place? Well, my guess and is that my humble opinion, right, is that when we try to understand quantum turbulence in low-dimensional systems, either one-dimensional systems or two-dimensional systems, we have to deal with topological effects, right? So if you are talking about wave turbulence, or turbulence that is that only involves mixing between these low-lying excitations, for example, Bogoliubov modes, you can describe these with this so-called Kolmogorov cascades, and you can also work out the Zakharov kinetic equation. So everything is more or less well established. But when you talk about strong turbulence in low-dimensional systems, you have to worry about the nucleation of topological effects. So in 1D, what we have are solitons. So we have these phase jumps in your system, and in 2D, we have these phase singularities, as already explained by previous colleagues here. Okay, so this, when you're talking about a scheme of generating turbulence, there will be for sure many of those objects appearing, right? And they were located randomly and distributed in your system. So they are not arrays, perfect arrays, but what you we can abstract our understanding of this system and talk about vortex and soliton gases, right? Respectively in 2D and in 1D system. Okay? So this is something that is very, is not explored at all. And we, of course, you can always run very lengthy calculations on the computer and try to see the emergence of these cascades. It's okay. But do you really understand what's going on? Do you really grasp the mechanisms between these energy cascades? What is really going on? For example, if we do the parallel with weak turbulence, we understand what's going on in weak turbulence more or less, because we know that there is this mixing between modes, and we know that this mixing between modes will result in some Rayleigh, for example, cascade. But in the strong turbulence regime, we don't really know what are the mechanisms. We observe either experimentally, for example, with Vanderlei did and collaborators, or theoretically, right, in the computer. But do we really have a theoretical framework to describe? I don't think so. Okay, that's my opinion. So from the other side, these kind of techniques, kinetic tools, allow us to explore out of equilibrium features that remain so far unexplored. For example, imagine that I want to describe out of equilibrium dynamics of Kachenko lattice, for example. If I have a system in thermodynamical equilibrium, things are more or less well understood. But if I go out of equilibrium, I don't really know what's going to be the overall dynamics of vortices in out of equilibrium dynamics. Okay, so this is an extra motivation. And then, of course, we could also talk about applications in quantum information, because as you probably know from liquid helium, at least people that are more familiar with liquid helium communities, they have thought about this impurity, putting impurities in the system to tackle the dynamics of these vortices. We don't really need these in cold atoms laboratories, because you can do more or less nowadays in situ imaging. But we can think of these impurities as an element that we can play with to do quantum information. Okay, so there are some works where people use these impurities trapped within these solitons or vortices as qubits, elements of logic. Okay, so there are lots of interesting lots of motivation, at least that are enough from it to pursue these activities. So let me start with the solitonic turbulence. So Patricia told us about bright solitons, or a certain special particular family of bright solitons. But here we are going to focus on the dark solitons. So dark solitons are depletions on Bose-Einstein condensates. So are nonlinear waves that result from a detailed balance between kinetic energy, interaction energy for repulsive system. So the only way for you to create a notch in this system is by producing a hole, right? So you pierce a hole in the system, and this is a density map that you have here, and they are characterized by a certain velocity. So there's parameter, which is velocity, characterizing the blackness of these solitons. I will describe more mathematically in the following, that describe the relative velocity within the fluid. Okay, so if C is the superfluid velocity, is the sound velocity, the local sound velocity of your Bose-Einstein condensate, imagine a 1D system. Everything here has to be thought about experimentally in terms of what is quasi one-dimensional system. So I have this transverse trapping that regularizes your interaction constant, and this G that is regularized then allow you to define this C. So you have two kinds of particular collisions. For example, if you want talk about solitons, the first one is this non-crossing situation where the velocity is below the velocity of each one of the solitons lays below the critical velocity. So say they are subsonic, so they just approach each other. And let me see if I can point here a little bit. You see that, so they start with a certain distance. Okay, here, and then they at this crossing point they cross, but they collide at this point, but then they repel again, right? So they don't really cross. But there's another thing, which is this situation, the supersonic regime, if you want, where there are this crossing. So if each one of these solitons have a velocity of 0.5, which means that in the center of mass they have a velocity larger than c. In the supersonic, they cross each other. So this kind of feature has to be captured somehow dynamically in terms of effective potential, right? So there should be, if we want to think about the centroids of each one of these solitons as a particle, so then there should be an underlying emergent classical Hamiltonian description. So that's exactly what I'm trying to do here. So we start with a variational ansatz. This variational ansatz is an ansatz for a kink anti-kink solution. So we have in the density plot, we have these two notches that are produced separated by a variable y. So this is the distance that we keep. This distance is dynamic, okay? So the separation between these two solitons is a dynamical variable. And we can construct a Hamiltonian from it. So, and this is done semi-classically. So we go Gross-Pitayevsky, we apply these ansatz, we do the regular calculations, and we get something which is the classical equations of motion, right? For the momentum, for the reduced position, and for the momentum. What is interesting is that if you do this classical perspective or this classical description of dark solitons, they are like whole-like particles, so they have a negative mass. This is very important because this negative mass that you have here is pretty much the mass of each atoms times the volume, right? So this N0 times C is the volume more or less occupied by this soliton. Okay, so this is the depletion. This is the negative mass of each one of these solitons. So if we, for example, have very well separated solitons, just to start with this situation, we get that the kinetic in the Hamiltonian that we get from this system, so we don't really have interaction, is twice the single soliton's energy, and is given by this quantity here. Beta is V over C. Okay. But then if you approach a little bit the solitons, they start to feel each other. And this is the important piece that we require towards the construction of a kinetic theory is that if I have a bunch of solitons, I will try to see that in the first approach, what I have is that the overall interaction felt by all the solitons is a convolution of the distribution of solitons over these pairs soliton collisions. Okay, so for this we need this potential, and this is the form of the potential. You see that for completely black solitons, beta equals 0, we have this kind of potential. And this is slightly different from what is explored usually in the literature, because people always assume that the solitons are very, very well separated apart, and they only see this exponential part here. But this is not the case. As we saw in the numerical simulations, if they cross, we cannot rely on an infinite barrier. So that's why we have this finite value here of the potential, okay? And we see that this is not a potential, this is rather a pseudo potential. And this is a pseudo potential because this potential depends on the velocity, okay? And it's easy to understand because if the solitons are faster, they are less deep. And if they are less deep, they are less massive, right? So the relative strength between the two solitons are given by this. So what I'm plotting there is the average velocity of the solitons, okay? So it's not really is pretty much the same, the potential, if you get the same, if you plot in terms of the average velocity. So with this in hand, we can go to what we call a macroscopic density. You can construct a microscopic density. So this is, for example, a simulation just to illustrate what's going on. Imagine that you have a bunch of solitons. At a certain point, you see that they start to bounce. So there's a dance of solitons here that is completely incoherent. Of course, microscopically, there are also production of sound waves, but for the moment, we are not taking this aspect into account. Okay, so we just mean field. We have a bunch of dark solitons, and that's what we are capturing with this function here. So the microscopic density that is calculated at position y and momentum p is something like that. I collect every soliton that is located at position y, every soliton momentum pi, and then I collect at certain value p and x. So I construct this microscopic density. And I need to get an equation that governs the evolution of this object that we call the Klimontovich equation, which is inspired by the approach that we usually in plasma physics is, for example, very well known. Okay. But what is important about this equation is that we have this V potential that is there. Okay, so everything is, the first two terms are purely kinematic terms. The term that are here involving interactions is this third term here. And this term is as a convolution between the pair solitons and the distribution. So it's a coarse-grained, if you want, a coarse-grained interaction between these systems. Oh, sorry, But the original distribution is very peaked. We cannot really do calculations with this one. So what we do is we do an equation for this ensemble. So this is a formal decomposition of this. So we say that from one side I have this average distribution over all realizations of the system plus a fluctuation. And everything that is fluctuation of first, second order in the fluctuation, because the averages in the first order are zero, right? So is the average value of an oscillating function is zero. The average function of two oscillating functions or the product is not zero. Have a correlation, right? Gives, right? So correlation. And the second term is what we call the collision integral formally, okay? Which are not, we are not going to explore in much detail because it's something that is still under construction. But the thing is, if you go to the equivalent of a dilute soliton gas, okay, so we have many solitons, but they are more or less separated. So we can eventually neglect this collision integral. And so that's what we start with. We start by neglecting this equation. So formally what we get is some sort of Vlasov equation. For those who are familiar with kinetic theory, the Vlasov equation is an equation governing a system. Typically it was developed for long-range interacting particles, for example, electrons in a plasma. But formally, we can use this and adapt this form of potential for our case. And our potential is not long range at this time, is short range, because it's, as I showed you previously, the interaction potential, let me come back here. So this one is of the order, so it goes away after some healing length, right? So this is the typical situation that we have for solitons, the short range interactions. So you already may think, for those who are familiar with consequences of long-range and short-range interactions, that if we are going to think about collective excitations on the sector of the soliton gas, because of these short-range excitations, we should expect acoustic dispersion relation, right? So beyond the dispersion relation that we have usually in the system, which is the so-called Bogoliubov excitations for the lowest, we have another mode, if you want, so a first sound of solitons. Okay, so that's what we are aiming to capture with this description. Let's see how it is done technically. Well, what the variable that we have to control the dynamics, the kinematics of each one of the solitons, for which we can control this distribution, is the velocity, is not the momentum. But fortunately, because we have a Jacobian transformation, we have this relation. So the mass that I told you is what relates, this effective mass is what relates the momentum and the velocity. Of course, if the system, these solitons are relativistic like holes, because they have this mass that depends on their velocity, right? So there's some Lorentz factor here. But if you start with the initial, just for purpose of illustration, consider a case of what we call a cold dark soliton gas, which is solitons that are prepared very close to dark state. So you don't really have to worry about the relativistic corrections to the mass. Okay. So this mass term here, which is a relativistic like mass, is just the regular mass that we have here. So the potential that I showed you that appears here in this kernel is a potential that is negative, so it should be attractive. But because of the mass sign, we have the mass that is negative, the overall dynamics is repulsive. So everything is okay. So this kinetic dispersion relation we can solve for some. It's of course a cumbersome object. You have the problems of the poles. We have to deal with the fact that we have to circumvent this and go with choose the Landau prescription to verify the causality in time. There's all of these technical problems, but for cold solitons we can really solve this analytically. Okay, but that's the good part. So we start with this so-called cold soliton gas, which means that we are going to start with F0 given by this water bag distribution. So there's a parameter, the VF, that we call the Fermi velocity, that governs this system. The Fermi velocity, why do we introduce this Fermi velocity here? This is intimately related with the fact that in one-dimensional systems, we have two types of excitations, right? So for those who are familiar with Liebig-Linear theory, you have the type 1 excitations on a Liebig-Linear gas, which are phonons. We have bosonic statistics. And then we have type 2 excitations, which are, I don't know, so far, people are trying to establish the relation with dark solitons, but for sure they are fermionic. Okay, so if you solve the beta ansatz for the problem, you get that the statistic of these type 2 excitations are fermions. And what is interesting is that now there are some authors claiming that establish this relation between the type 2 excitations in the Liebig-Linear gas and the dark solitons. So this is very funny because we are doing a more or less semi-classical physics, in the sense, well, mean field physics, not semi-classical, but mean field physics. And somehow we are able to capture the emergence of these quantum type 2 excitations in the fluid. This is amazing, right? So, mathematically, if we put all this together, we get this first sound velocity. Okay, so the dispersion relation that we get for our soliton gas is something like that. So V1 times K. So it's given by these parameters, and is controlled by this quantity N naught. N naught is the density of solitons, is the number of solitons that you put per each healing length, right? So it's less than one, typically, much less than one. So in principle, this quantity here, V1, is controlled by this dilution parameter that we have here, and is something that lays below the Bogoliubov sound speed. Okay, so this is the dispersion relation that you get, that you expected for this kind of system. Okay, so we were happy at the point to see that we could reveal some sort of collective mode in another sector, which is this dark soliton gas, and now we want to compare with the numerical simulations to see whether or not we have some quantitative agreement, right? So we developed this strange object of a kinetic equation that governs a bunch of solitons in the phase space, but we have to have some control of it. So to do that, we did some numerical simulation. This is a snapshot, an example of this one, and this is a visual manifestation, these red lines that you see of emergence of a sound-like mode, right? So for those who are familiar with these plots, you see that this is a manifestation of an acoustic-like mode, which is a mode that is more or less dispersionless, right? At least in the long wavelength limit. So let's see whether or not we can really observe this in the, this is qualitative view, right? So we need some quantitative things. So on top of that, you also observe that there is a formation of sound on top of the soliton gas. We see at a certain point, we are still working on, just a parenthesis, we are still working on the accuracy of these numerical simulations, because in the long run, the numerical methods can at a certain point fail. But let's say that we have some trust, even if it's not quantitatively correct, at least we see that there is a formation of some sound waves on top of this. So this is the problem that we have to deal at a certain point, right? So it's not only the soliton dynamics, but also have to deal with these phonons on top of this soliton gas. To do some quantitative agreement between the numerical simulations and our theory, we did direct numerical simulations from the Gross-Pitievsky equation. So we just grab some configuration, some soliton gas that you put there with phase imprinting method. You do some imaginary time evolution, and then you do some real-time evolution to see how the dance of these solitons, right? And you see, this is exactly what we get if after we do the static, the dynamic, we extract the dynamical structure factor from the wave action, and we can get these features here. You can observe two interesting facts there. Is that for those who were who are familiar with this, you can see that first one is the Bogoliubov mode, or very close to it, right, at a certain point, and the other one is a mode that we associated to this soliton collective mode, but lays here below this as an energy that is lower than the Bogoliubov excitation. What is interesting is that we also have a deviation from the Bogoliubov excitation. So we would expect some Bogoliubov like a dispersion relation, but this mode is stiffer than the regular Bogoliubov excitations, which means that we have a regularization, right, of this sound velocity in the system because of the presence of this soliton gas. Okay, this is very reminiscent of what Hewlett presented yesterday. It's a completely different situation because we are not talking about spin charge separation, but somehow we have some whole particle separation here in terms of spectrum, right? So it's very interesting to make and this is also an aspect that we are investing some efforts trying to establish the relation between this approach and the physics of Liebling gas in 1D. Well, but this we're happy. By the way, this vertical line here is the validity range. So we don't really trust the result after a certain point. And this has to do with construction, because you remember that to obtain these results, I neglected this collision term, right? And the collision terms are important when the density of the gas are very large. Also, the wavelength limit n0, so the k wave vector has to be larger than the separation of the solitons. Otherwise, I cannot do a mean field approach for the soliton gas. I cannot really talk about a collective motion, right? So this vertical line is when this description is not completely accurate without the inclusion of collisions of solitons, for example. Well, so this mode that we don't know, for example, this deviation of the Bogoliubov theory is something that we suspect that can be resolved after we do a beyond mean field analysis, right? So if we now have an equation, imagine that we do this kind of approach, we do a kinetic equation governing the soliton gas, but on top of that, we also take into account the dynamics of the sound waves. Now, the sounds that are the sound waves that are propagating the BEC see a modulation in the density to the presence of these solitons. So effectively, they don't see the N naught, the infinity density, right? So we have some sort of local density modification of the sound velocity of the system, and this has to be integrated out. Of course, we can do some sort of let's say poor man's analysis, but this requires really a detailed analysis, right? Because we have to find an equation for the sound wave. So, for example, the Bogoliubov excitations on top of a soliton gas, and this is a complicated problem. Okay. But the more sophisticated thing to do actually is to get a kinetic equation similar to this equation for the soliton gas that I showed you previously for the sound waves. Okay, and this is something that we are thinking of. Oops. So this is the scenario for soliton turbulence. So what is, before going to this vortex, this part 2 of the talk, what is really the extraction of this? What is the take-home message of this thing? Is that if one day, if I want to do a really experiment in 1D systems producing strong turbulence, I will for sure produce soliton gases, right? So incoherent soliton arrays with not only they are not going to be dark, there will be a distribution of velocities. So therefore there will be a distribution or let's say a more a thermal distribution eventually for these solitons in the beginning, and these solitons will evolve according to these equations, and we will merge with the solitons. So our perspective of what is going to be a strong turbulence model is something that could be done in terms of weak turbulence models. So you can think about the weak turbulence procedures applied to a gas of dark solitons. Okay, so now we have this wave mixing process that you have in weak turbulence, but on top of a soliton gas. So this could be a way to do strong turbulence, right? So we just have to abstract a little bit our system and try to think about solitons, treat the soliton sector as a separate product. Okay, so this is a separate object. The soliton excitations are a separate object, and now I do the same techniques that I do for sound waves for these waves on top of the soliton gas. This will be very curious. I wonder what kind of cascades we will find for solitons. Okay, so if you go to two-dimensional systems, the story repeats. But now, instead of having solitons are dynamically unstable. For example, dark solitons are dynamically unstable in 2D. But what we have is the equivalent of that are the vortex. Okay, so they are slightly different objects, and these objects, of course, are characterized by a singularity in their phase. But there are several ways to do this, and Bagnato showed many. For example, these shaking techniques allows for you to produce vortex in three-dimensional systems, but in two-dimensional systems, well, there are probably some tools that can be applied for Bose-Einstein atomic Bose-Einstein condensates. But there are these emerging platforms, which are these quantum fluids of light, where you could probably do this in a much cheaper way. We are poor, we don't have money to have a VEC experiment in Lisbon, so we are trying to produce an experiment with quantum fluids of light, where they share this analogy with Bose-Einstein condensates, right? As Feynman told, same equations, same solutions, right? So the system are governed by the same kind of equations, which are, this is the equations governing the a beam propagating in a Kerr nonlinear medium, and they share the same physics, the same form of the Gross-Pitayevsky equation. So one scheme that we are thinking of to produce this turbulence in two-dimensional system is this colliding. You consider two initial condensates. Let's talk about condensate just for the fineness of language, that will collide against each other. Okay, so if these two condensates collide against each other, there will be some region where there's some dynamical instability that will be produced. This dynamical instability will result in something that we'll see. And then this dynamic instability will deposit energy, will distribute the energy, and eventually produce a cascade. Okay, so that's the spirit. To be analytically or to analytically predict this, what we did is just to perform this Madelung transformation that allows us to go from the wave equation to a bunch of quantum hydrodynamical equations. And with that into hands, we can do the analysis, the stability analysis, and we observe we have this two-mode dispersion relation. It's just some complicated dispersion relation, but it's something that you can do straightforwardly. And those are the features of this dispersion relation. You can see that depending on this beta, which is roughly a parameter governing the velocity of these counter streaming beams, you get this kind of situations here. So there's an imaginary part in the spectrum. Okay, so there are a bunch of wave vectors that are dynamically unstable, which means that are some modes that will grow in time. Okay, so this is the onset of this ability. And to check that, we performed some numerical calculations and we observed exactly this. So initially the superposition of these two beams will produce these fringes that then will develop into dark solitons. But these dark solitons now are in 2D and they are dynamically unstable. So the fate of this bunch of dark solitons is to break down into vortices, pair of vortices and vortices. And at certain point they will produce this kind of patterns here. Okay, so this is what we expected from the numerical simulations. And by computing the wave action, we see that there are the formation of some cascades here. So we were very happy with this scheme because we were more or less convinced that this will result in some sort of turbulence. To be more exact on that, we separated the two components of the energy. So one part, the incompressional part, so the incompressional part of the spectrum, and on the other side, the compressional part of the spectrum. And you could observe exactly the emergence of these cascades here. So this is the usual Kolmogorov cascade. Then you have this entropy part here, K2-3. And then in the compressional part, you also get this signature of -3/3, which is typical from the Zakharov cascades for weak turbulence. So we can produce either vortex turbulence or sound turbulence, if you want, or wave turbulence. Okay, I will not focus much on that one. I just wanted to see if this is possible to do with quantum fluids of light. Of course, all these ideas could be transposed to Bose-Einstein condensates, and indeed we wrote a paper a few years ago on that, but nobody really gave too much credit on that. Colliding 2B sees to see if it was a way to produce this, but just probably I can discuss with the experimentalists on the room nowadays. Probably they are more convinced now. But the communities in the quantum fluids of light community anticipated this, and they did this with the experiment. Just before we go, let me see if we can show you the simulations. Those are the initial conditions, and then you see the formation of these dark solitons that break into vortices at a certain point. And this, of course, there is some grayscaling problem here, but you can, let me come back again. So you start with two solitons, two condensates, and then you collide them. You see the formation, so the formation of this interference pattern that goes into dark solitons and then break ultimately into this vortices. So controlling the speed, you can control the injection energy point, and you can control also the number of solitons, and consequently also the number of vortices that you produce in your system. Okay, so this was appealing enough for our colleagues in France, in the group of Alberto Bramati and Quentin Glorieux, to do these experiments with quantum fluids of light. So they have this very, very easy, very appealing scheme to do this. So they have this special light modulator that produces these phase defects, these phase patterns that puts the velocity, that initializes the velocities that I told you, these two counter-propagating systems. and then they could observe at a certain formation of some time the formation of these patterns. We were very excited when we saw that this could be done in the lab, and we discussed with them, and you can see that more or less qualitatively we get exactly the same features that we saw with our scheme. So we were very happy to propose to the experimental community a scheme based on this two-stream instability. By the way, this two-stream instability is very familiar from plasma physics. So people working in plasma physics, they have this to deal with this work every day. And it's a very prominent phenomenon in astrophysics, for example. Okay, and they know that these two-stream instability in plasmas are relevant to produce turbulence. So we got some inspiration from the plasma physics and applied here to this. So that's where this idea came from. Just to give you some historical note on that, why we did that on the first place. Okay, so then they observed this again. So this is what those are experimental results in the incompressional part. You can see that this is where the region where the injection is done. The injection is done here, and you see the formation of a direct and inverse cascades into this Kolmogorov range, and also the observation of this chi-3, which is the entropy. I think is the name, is the characteristics of the vortex turbulence. This is very, very, very nice feature. So you have the authors of this paper describe these three features of the spectrum as single vortex. The single vortex cascade, which is a cascade that is produced inversely as well. Then a Kolmogorov inverse cascade, the classical part of the spectrum, K2 -5/3, and then this vortex core cascade, K2 -3. For some reason, they did not observe the deep Wien quantum turbulence spectrum, the K2 -4, but I suspect that is a matter of resolution. Or probably this scheme is unable to produce this kind of spectrum. I don't know. So this is a question that I would like to discuss with you. I don't really have a clear answer for that aspect, but I'm open to discussions, and I will be very happy to if you can shed some light in this problem. But at least you can observe some clear signature of the vortex dynamics here, which is very, very interesting. So conclusion is that at least with the conditions that quantum fluids of light allow, we can observe the formation of this quantum turbulence in the vortex for vortex gases. Okay, again, this motivates us even further to do the same thing that we did for solitons with vortices. And we have this object with this random distribution of vortices in our superfluid, and we want to see how they behave. So for that, what we do is we start with a point-like vortex model, as Monica introduced in the yesterday. Just before going to just to avoid the complications of Gross-Pitevsky equation, we are interested anyways in the incompressive particle of the spectrum. So we don't really have to worry much about the aspects of the soliton core for the moment. Okay, so this is the interaction energy between two solitons, or each pair of solitons. They interact with this interaction, and this interaction is long range, right? This long range interaction is very interesting, because systems with long range interactions, if you look for excitations on top of systems with long range interactions, they are not sound-like, they have a gap, right? There's a cost of energy to produce excitations in system with long range interactions. So this system is much closer to a plasma, if you want, right, two-dimensional Coulomb gas, than what solitons did. And solitons are completely different, because their interactions are short range. So that's why no wonder we have these sound-like excitations for solitons. But what's really going on with the vortices is completely different. Not only that, but also under the technical point of view, we cannot assign a velocity. So the relation between momentum and velocity that we have in solitons is not pathological. Velocity is related. There's a mass transformation between the velocity and the momentum for solitons. Here is not the case, because the momentum and canonical momentum and the positions of the vortex are related by this Levi-Civita. So they are the same spatial dimensions, but they are just orthogonal in that way. Okay, so the presence of this object in dynamics complicates a lot our life. Okay, so if you want to proceed again with this kinetic description in terms of a Montovich equation, we can do formally, But at a certain point, what we get is these complications associated with this, not so far, because so far is formally written in terms of this acceleration. So this collective acceleration, okay, this object that appears here is just a convolution of this log term and the distribution function, okay? So far it's formally okay, but then the problems arise when we go to the linearization of this equation. Just a more technical remark here. See that we also get the same structure as previously, so we get fluctuations here, second order fluctuations that we can also neglect for the moment. There will be a mess when we have to deal with them for the vortices, but for the moment we just get into this form. So the smooth version of the Klemontovich equation, we also call Vlasov equation. And now probably historically with more property, because we really have long range interactions, so we can safely call this equation a Vlasov equation for vortices. So what are the consequences of this? Let's do some mathematics. We do proceed some linearization. So we start with some background that we start. So we treat this as an initial value problem. Okay, we produce some vortices in the system, and now we let them evolve. And we distributed them according to some special distribution, which, for the reasons that I told you, are intimately related to the distributions of momentum, okay, because of this transformation. So if you do that, we get this fancy kinetic dispersion relation that you can evaluate in terms of these Fourier transforms. And at the end of the day, we get the so-called plasma frequency, which is a universal result for this collective excitation. So gamma is the circulation, and N naught is the concentration. Okay, is something that is over, is the number of vortex per unit area. And you see that there is a gap in the system. This is the collective excitation of the system. And that's why we so far have not observed in our numerical simulations. I just wondered why, because this costs energy, right? Is the reason. So if you let the system evolve dynamically and you do the static, try to see the dynamics of the vortex via some dynamic structure factor analysis, you won't see anything in your spectrum. You just see the Bogoliubov excitations, because this system, to excite collectively a gas of vortices, you really have to put some energy, right? So this is something that I have hoped to find a scheme. We have to find a scheme to try to observe this collective motion of vortices in the numerical simulations. Okay, so this is something that I also have to discuss with Arnaldo and other people who are interested in this problem here. A way to do this, at least numerically, how to excite this mode in the soliton gas, in the vortex gas. Another remark that is interesting for those who are familiar with the dispersion relation of electrons into the dimensional system, they would wonder, why don't you get the usual dispersion relation that is square root of k, right? So this, if you have an excitation for two-dimensional electrons, for example, graphene, people who are familiar with the physics of graphene, they would expect a plasma dispersion relation of something like that. Well, the case, it doesn't happen here because of the very problems, the nature of this interaction. Okay, it's not because of the log form of the interaction. This is not a problem, because the log is long range anyways, as 1/r. So you would expect a gap anyway. The thing is that there's this problem between the definition of momentum, the relation between momentum and position. They are not independent variables in vortices. Okay, while in electrons, I don't really have this problem. I have their mass, the velocity, and the momentum are related by P equals mv, and here is not the case. So we have problems to assign a mass to a vortex in the hydrodynamic regime. That's pretty much what I'm saying. Okay. So that's just why we should not worry much why you don't recover this square root of k in the dispersion relation, and rather this gapped mode here. So before we go, some conclusions and perspectives about this whole story. So from one part, we show that there is some collective behavior of solitons. So solitons are, we can put one soliton, two solitons, three solitons, but when you put n solitons in a condensate or a one-dimensional fluid of your taste, you have a collective emergence of collective motion. Okay, and this collective motion can be described in terms of this kinetic equation safely. Vortex gases can also we can also do the same with vortex gases, or at least try, but they are trickier in the phase space because we have to deal with the fact that these canonical relations are a little bit pathological. Okay. For the case of vortices, we have to deal with long-range interactions. And what would be interesting now is to test not only for cold gases, but for thermal vortex gases. For example, imagine if I really want to go out of equilibrium, really out of equilibrium, or we can start to think about, okay, now I will try to do what people in statistical physics do. I start with a situation that is close to thermal equilibrium. So I go to thermal equilibrium, I need some thermal distribution for these guys, right? So what is going to equivalent of a Maxwell distribution for a soliton gas? I don't know. Okay. What is going to be the equivalent of for the vortex gas? Okay. And then this could be to the starting point to start to analyze what is going to be the thermodynamical features of this. But if you go to out of equilibrium situations, imagine, for example, you have distributions that are completely crazy, as the ones that you would suspect to produce in real life turbulence schemes. Then you have a tool to evaluate these situations with in the kinetic formula. So these kinetic equations are able to evolve the distribution functions of these objects, either solitons or vortices. Okay. But of course, all this has to be compared with intensive numerical simulations because we have to benchmark these models. We are coming with these kinetic equations. There are not much done in the literature, so we really have to fight to establish these descriptions within the communities. Then we also have, but all these that I told you are consequences at the mean field level. But then we have to go beyond mean field. And going beyond mean field, and that's what this connects with what I told you in the beginning, that if you want to go to a more quantum description or beyond mean field, you can either do this classical or semi-classical. You can quantize this object or not, so it depends on the treatment that you are you're doing. But you have the soliton gas wave function plus fluctuations. So we can this part is more or less well treated, but then we have this thing. One way to do that is via the Wigner transform of this object, right? So we calculate the fluctuations and then we do this staggered convolution and we go to phase space via this Wigner transform. So then the problem of this would be a two-fluid model, right? Where the two fluids now is a fluid for the soliton gas governing a two-gas model, if you want, right? So I have a sector describing these low excitations, the whole-like excitations in the system, and then another one describing these particle-like excitations or Bogoliubov excitations in the system, okay? So sound, in other words, sound waves and soliton waves, okay? So I have two kinetic equations that will be coupled, and they will describe. This will be, if we are able to describe this will be a full description of this system. So we have a full phase space description with all the microscopy that we need to understand the processes in quantum turbulence. Okay, because in strong turbulence in low dimensional systems, I do not expect anything but these objects: solitons or vortices, regardless if you are depending if you are in 1D or 2D, plus Bogoliubov excitations. Okay, so if you have a theoretical framework that is able to capture all this, we can do everything. So the hope is that one day we'll be able to answer to an experimentalist or or someone doing pure numerics, why do you observe this k to minus 3 cascade in your system? Well, because there are some processes in this sector that are of this form, for example, wave mixing, that allow for this. Okay. So it really will boil down. What I want to propose here is to draw your attention for the need of a microscopic description of turbulence in terms of this increasing a little bit abstraction level. Okay. So this is one of the conclusions. But now that's why I have in different color. Seeing the talks given by the previous colleagues, and especially in the last day, where people are interested in these curved manifolds, this could be a nice way to motivate these manifolds, curved spacetime, to motivate these dynamics of these topological objects on top of this curved surface. So you can imagine one day we'll be able to have a kinetic equation describing, we have a mechanism to do some analytics to some extent of ensembles of vortex on a sphere. This would be amazing, right? At least I would be very funny. I would have lots of fun trying to do this kind of calculations. Just an extra to show you another effect that we have been interested in is the so-called, we had problems in the literature, okay, so it's not very well established. We call this Casimir effect, but some people in the literature didn't like them. Probably some of you in the audience criticized this work, but the physics goes like this. Imagine that you have a vortex dipole, and it's not the regular vortex dipole. This vortex dipole is living in a turbulent condensate. So this turbulent condensate is wave turbulence. Okay, so this condensate contains subwave turbulence, and now I have two vortices. What happens is that at certain time, these vortexes will dance. Not only that, but they will spread apart. Okay, and this is a feature that we want to attribute, that we try at certain point, we try to describe this with the emergence of a collective force, an effective force that appears between these two guys, that is due to this wave turbulence background. And we call this somehow, it's reminiscent of the Casimir physics, because, and why we do that, because the way we did the calculations to extract this force is really based on this concept of regularization of infinites. We have an infinite pressure outside the system and infinite pressure inside the system, and if you subtract these and regularize, you get a net force. Okay, it's really in the same spirit of Casimir. Okay, so imagine that you have these two guys. If they have zero sound on top of them, they will just do this orbital motion, which is typical for a vortex dipole, right? As probably know in the mean field. But if you have excitations, some spectrum, there will be some sort of energy difference between what happens between the difference of energy pressure between in inner regions and outer regions that will promote this spread of the vortices in the system. Okay, so this is another perspective of these vortex sound interactions that we could tackle in the future with these kinetic equations once we have this full thing. And the other thing is to do with vortex thermodynamics. There's this beautiful paper by Gauthier and al. That was published in 2019, putting in evidence that we can have these negative states of negative temperature states for vortex gases. So if you start with certain amount of vortex and anti-vortices in your systems, at certain point they will. How much time do I have left? Oh, I have to conclude, right? Okay, I will. These vortices will bunch together and form these two big vortices, and that's what people call Bose-Einstein condensation of vortices. Okay, so these vortices, if you think about these vortices as elements of another fluid, so as gas, so these two gases will go to a state that is close to these Bose-Einstein condensation to a vortex, and is characterized at the thermodynamical level within the Onzaga theory as a negative temperature system. So, and dynamically, the way to go there is via an inverse cascade. Okay, this is a very beautiful experimental demonstration of these intricate relations between vortices and also the notion of thermodynamical equilibrium. Okay? And with that, I conclude. Just to acknowledge the collaboration with my colleagues there in Lisbon, and this is a picture of my city, very close to the place where I live. So I live here near this cathedral, and this is the view that I have every day before I go to work. So thank you so much, and I hope you enjoyed.
Questions?
So at the beginning, you showed two different cases of soliton collisions. One where the two seem to avoid each other, and another where they cross.
Mm-hmm.
And you ascribe that to a difference in velocity somehow.
Mm-hmm.
So how does that work? Because normally I would think about describing a wave with an amplitude and a phase.
Yes, that's it. But that boils down to it. The thing is that you describe, this is when you do the microscopic description in terms of the Gross-Pitevsky equation, you really have to go to wave function. The thing is that when you do the reduction to the particle-like so the classical picture, what happens is that you have two centroids. You can abstract the wave function, and you have two centroids that will collide and go away. This is when you do that in terms of classical picture, you require a potential, right? You need a potential for these particles. And this potential is emergent from the variational ansatz that you get from the Gross-Pitevsky equation. So you plug the wave function with the two solitons in the Gross-Pitevsky equation, and you extract the Lagrangian from it, and then consequently the Hamiltonian. That's how you do it. Okay, so it's an emerging dynamics of these point-like particles, which is necessary for you to increase the abstraction and then go to the phase space description of vortices, of solitons.
Okay, thank you.
But numerically, I agree. Numerically, that's how you do it. You really go to you solve this. Those are numerical simulations.
Thank you very much, Hugo, for the nice presentation. I have a question. When you have the light, at the end of the day, I end in the decaying of the turbulence, I end with what? With a thermal light? With what I end at the end of the process?
That's an amazing question. That's a very good question. I mean, we know that for sure, this vortex, we cannot only excite vortex turbulence, we will excite also wave turbulence. This is one of the aspects. But in terms of the temperature of the system, we don't really know. So if we have some theoretical, let's come back here. Under the theoretical point of view, what we expect is that for the compressional part of the spectrum, you get these. So this is the theory, right? So I can only commit to the theory here because the experiments were done by other group. So you see these kind of things, right? So there's this formation of this turbulence. So you have this equivalent. If you look at the wave action, we get some Rayleigh spectrum for the waves, for sound waves. But for the vortices, what you get is this here. So I don't know if this answer to your question is somehow. So what I expect is that the sound waves will be some sort of out of equilibrium system as well. Okay, so there is.
Well, but this is out of equilibrium stuff.
Yeah. So so I don't produce a thermal cloud of phonons.
But at the end of the day, this should return it to equilibrium somehow if I don't do it.
Yes, I agree. But we don't see this in these runs. I don't see.
And then I have a comment. Is relative to the sound waves on the
Solitons.
evolution of the turbulence, either solitons or, for me, soliton is a guy that could not make enough to be a vortex, stop the phasing pi, or, but they are very equivalent. I mean, the sound waves is a very important background ingredient for the evolution.
Yes.
Even though we don't know, and theoreticians do not give us a very good hint, but we all know that that's very important. That's why we see very big deviations on the evolution that we cannot understand. It's nothing to do only with reconnection. It's nothing to do with the evaluation, how the total amount of vortex length decay with time, but that is something else. I don't know if Nick can comment anything about this, but.
Yeah, I totally agree. That's what actually, even at the quantitative level, we really need to do a full description of this. Will involve a detailed analysis of the sound waves interacting with solitons. So, and this has to be done at statistical level. So solitons alone do not explain the whole physics. But what we could do so far is to show that there is this new.
Yeah, and I think presence of sound maybe will retard the evolution.
It depends.
Not only speed up, but this is only feeling.
That's complicated. If you have only one soliton or two, you can tell this. But if you have n solitons, it's complicated to guess. I mean, at least I cannot.
And about the paper you mentioned, the science paper on the ONZAG, this is predicted, right? That we would have clusters of vortices and antivortices, which is called the anti-cascade or inverse cascade. Okay.
Yes, this is predicted. Yes, but this was the first experimental observation.
Yeah, which is. I think there is a guy in New Mexico that he did something before, but I think he's referenced in this paper.
The Gautier paper.
Yeah, there are two papers back to back in that science issue.
Yeah.
One is by
Tapio Simula, and the other one by
the other group from they are both from Australia.
Yes.
Okay.
One is from Tapio Simula, and the other one is, I don't know the name.
Chris Helmerson. We know
Probably,
him very well.
Yes. Yes.
Ladies first.
Hey, Hugo, thank you for the lecture. You said in the middle of the presentation that it can happen some interference in velocity between solitons, right? My question is, how can you explore this interference, and what if there are other kind of interference in these solitons, just velocity, or can you observe other kind of interference?
That's a nice question. So the thing is, this initial the dynamics that I showed you was just to explain the two kind of features that you have, right? So this is what you observe in dynamical simulations. If you go to Gross-Pitevsky equation, just prepare two great solitons with velocities in this range, and you get these two features. One, the solitons just go and collide and then repel each other, but they don't cross. And the other one means that they cross. But for us to understand that, we have to understand this in terms of kinetic energy versus interaction energy. So if the potential depth is deep enough, so potential is deep enough, and the kinetic energy is low enough, they just go there, but they not cross the barrier, right? So if they are fast enough, they cross, and the reason why they cross has to do also with the fact that the barrier diminishes. With this potential is complicated. It's not a potential that depends only on the position, but depends also on the velocity of these particles. That's the problem, right? So the fastest are the solitons, the weaker is this barrier. So that's why at a certain point they cross each other. Okay. But that's at the mean field level. Again, as Vanderlei was pointing out, the fact that we have sound waves, we have additional forces here that can either retard the soliton or push the solitons. We can kick the soliton with the sound. So there's in condensed matter physics theory, there's a vertex, which is the vertex interaction between a soliton, and then emission or absorption of phonons. Okay, this vertex has to be done. You have to do the calculations of these vertices and put back into the dynamics. Okay. And also the mediated interaction. So we have two solitons sharing a phonon. This kernel, we don't include these kernels. So the field theory remains to be done. Okay. So those are the aspects that had to remain to be treated in a quantum formulation of the problem.
Okay, so is it possible to share information?
They will share. They will
so
share.
you can get manipulate
Via the sound.
information
Yeah, yes.
in this way.
Yes. But
Okay.
so far, what I did is just to treat the mean field part of this whole complex interaction, right? Which is already complicated in the system that you have many solitons and vortices. Okay.
Okay, thank you.
So welcome. Thank you.
In the breaks. Thank you. Let's thank again the speaker.
So we are 15 minutes late, so I think it's better we return 2:15, okay? So as we can enough time for lunch. So 2:15 we return, okay?